Okay, we might be live. We might definitely be live. Hello everyone. Can somebody write in chat with a note saying, hey, sound works, etc. So today is a special stream because Vulkan 1.4 was released on Monday, Tuesday, whatever day it was released. So the previous kind of point version of Vulkan 1.3 was released a while back. I don't recall when, but like a couple years ago. And we have this tradition where since 1.2, I guess, or 1.1 maybe, whenever there is a new version of Vulkan, I do a stream where I talk about the new features in the point version, why they're necessary, why they're interesting, sometimes why they're not interesting, and it serves as like a good way for people to be able to orient themselves in the new version, because whenever you read 1.4 has a good sort of documentation page on Chronos website that talks about why they did this and what features are there, but it's still the case that you're looking at a list of like features or extensions, sometimes with little justification or with little obvious justification from just this overview as to why that happened. So we are going to talk about kind of all of the 1.4, the release. Thank you, people. The release this time. There's no surprises in the new version in the sense that this version is mostly sort of extensions that have been promoted to core, but I think it's still valuable to talk about these extensions because people might not be aware they exist, etc. And also there's a bunch of required features that have always been part of Vulkan but are now an critical sort of part of 1.4. You can't ship a compliant implementation of 1.4 without supporting anisotropic filtering, for example, which has been a GPU feature for like 30 years, but you can't, or like, you probably don't want to ship a modern renderer without anisotropic filtering. So I think there is this sort of two aspects of Vulkan that we'll talk about, Vulkan 1.4 that we'll talk about. We will not write any code on stream. We will draw and write a bunch of stuff on stream, and then we will sort of refer to a lot of the extension pages to figure out why some of these things exist. All right, so let's go. So the plan is, let's talk about kind of two halves. The first half that we'll talk about is just briefly touch on let's briefly go over just all of the features that are now required in 1.4 to support that have been core features before, because this is just just like gonna give you a quick overview of why some of these things are interesting. And then we'll talk about the new core functionality, which is essentially the promoted extensions. And some of them are kind of interesting and some of them are not super interesting. And more features. And even more features. Okay, so let's quickly talk about things that are now required. So whenever you write a Vulkan renderer, you pick a version that you start from. Let's say you pick the version 1.0. And then you create the device. When you create the device, you say, oh, I want to use these specific capabilities. And Vulkan 1.0 guarantees you relatively few things. 1.0 is close to a decade old. I think it released in like 2016. And so it's the end of 2024. It's going to be a decade soon. And when it launched, a lot of the hardware at the time, especially on Android, on mobile, that was the target, supported OpenGLES 3.1/3, sometimes 3, sometimes 3.1. I think the unofficial target sort of was 3.1. This means that there is a bunch of things that people on desktop have kind of expected to be the case for a while with Direct 3D11 and stuff, but just wasn't a baseline on mobile. And so 1.0 shipped without requiring a bunch of things. Let's look at the few things that are now required. So now, if you're writing a modern renderer and you require 1.4, these are the things that you know you will have to have. 32-bit index support. It may come as a surprise to some people. Why is 32-bit index support like a required thing that we are talking about in 2024? But a lot of GPUs of the past have only supported, I think, 24-bit index buffers. So you say, I'm going to use a 32-bit index buffer. But actually, if you try to index past like 2 to the power of 24, which is like 16 million, this will not work. So now it does work. Arrays of cube maps are now required. Again, I think this is the D311 feature, but it's sometimes useful. For example, if you have some GI light probe implementations or some shadow map implementations use many cube maps, many small cube maps or many semi-large cube maps, and putting them in a texture array can be useful. The independent blend feature is referring to the ability to blend, to set up different blend settings for different targets when you do multi-render target rendering. If you watched the Niagara stream last time, we actually set up a G-buffer to do multiple render targets. And what happens when you have a G-buffer often and you want to blend something into it is you want to control things differently. So let's say you're rendering, you're rendering, well, what is up with this? Hold on. Let's do 3. Okay, so let's say you have albedo in your G buffer, which is like R8, G8, B8. And let's say you have something else like a normal, for example. And then let's say you want to render a decal on top of your G buffer that modifies the G buffer. But what you want is you want to blend the decal. Oh my God, there is like a car, which is definitely not my car, but somebody should. All right, cool. So you render a decal into your G buffer and you want to change albedo but not change the normal, or vice versa. This can be useful. Renderers that rely heavily on decals tend to have special modes for decals that artists can use to, for example, you have a concrete wall and then you want to render some sort of paint on it, but paint layer kind of shouldn't affect the normal, or at least not affect it too much, or sometimes not at all. But it should affect albedo greatly. And for things like this, it's convenient to be able to set up modes that say, oh, for albedo, we are going to blend it like this, but for normal, for example, we won't. So again, this is D3D like 10 feature, but it's now required to be supported. Sample rate shading refers to multi-sample anti-aliasing, an ability to run the pixel shader for every sample. This is useful when you have MSA and you have alpha cut or alpha kill or alpha test rendering. So you have a texture and then it has like a leaf. I hope people appreciate my amazing drawing skills. And you want to do an alpha rejection of every pixel based on whether the alpha in the texture is like less than 0.5 or not. If you do this naively, then with multi-sample anti-aliasing, the edges around this thing are very rough because you're not getting multi-sample anti-aliasing. There's a couple different ways to fix this problem, but one way to fix this problem, again, D3D 10 or 11, maybe 11 feature, is you run the pixel shader per fragment, so per sample. So for MSA 2x2, you run it 4 times, and then you do the same. You run the same code there where you reject individual pixels or samples in this case based on the values in the texture, and then your results are sort of. Alpha testing is now cooperating with multi-sample anti-aliasing. This is not the fastest way to do this. There is a more correct way to do this, which is to use sample masks. I don't know whatever the feature bit for that is. I'm not sure if it's forced let's see, it's something like, I don't know what it would be called, sample mask. I'm not sure. Anyway, but there's other uses of this. But multi-sample anti-aliasing in general, I think, is becoming less and less important for modern renderers for a variety of reasons. But it's still nice to have this. So this one is fun. When you use draw indirect, you can let's show the struct. So when you use multi-draw indirect, you specify this command that says, and there's a similar command for indexed rendering that specifies how many objects, how many like vertices to render, etc., but also how many objects to render, how many instances to render, and you can specify the offset for these. Which is sometimes, again, useful. Like, I don't want to go too much into details here, but there's some cases where you really want an ability to not just say, I want to render like 5 instances of this object, but also specify an offset there. And previously, this value could only be 0 unless you enable the feature that is not guaranteed to be supported. And now it's guaranteed to be supported. So depth features, so depth clamping and depth bias clamping, they're both important. Depth bias clamping is, so depth bias in general is an ability to say, oh, I want the depth of this fragment to change based on the slope of the triangle usually. Which is useful again for decals to avoid z-fighting. But the problem is when you do sloped scale depth bias and you have a triangle, if you have a triangle that you look at sort of from head on, then the slope is small, and so you have to offset the depth by sort of slope times factor. So whatever the value of the factor is, this function is fairly small, like the output is fairly small. But if you look at the same triangle at a very grazing angle, then the slope becomes very large. And in fact, there is not like a very practical bounds on the slope. And if you just use the z-bias, what can happen is you look at the triangle at a grazing angle, and the output of your bias, slope times factor, is very, very large. And if it's not tuned properly, you can actually see these objects kind of from behind walls, for example. Like you may have an object in front of this, and the decal or whatever should be occluded by the object, but because of this slope scale behavior, it's not. So you can now clamp this. The more valuable perhaps thing is depth clamp. This usually when you think of rendering triangles that are not that are like behind the far plane or in front of the near plane, you think, oh, these triangles should not be rendered. But when you work with shadow maps, you might want to limit your depth range to be much shorter than what the objects that you're rendering it into are. So this is called, there's like a term for this called shadow pancaking. This is literally because you're sort of taking the objects that are in behind the far plane, for example, and squishing them to all be on the far plane, which sounds useless, but for shadow maps it's actually useful because you care about there being an object or not in a given pixel behind the far plane, and you don't really care about the depth of this. And this is useful because this allows you to improve depth precision, because your depth range could be small. So like, let's say this is your depth range, and then you have objects here that can still cast shadows onto this depth range, but they don't affect the precision of the depth in that range. So that's useful. So anisotropic filtering, again, it has been a feature of the GPUs for like many decades now. You kind of want this for MIP mapping to not turn objects into mush at grazing angles. Now it's required. So this refers to an ability to write to random textures and buffers from fragment shaders. This is important for a class of rendering algorithms. It can be slow, but it also can be very important. Off the top of the head, for example, if you're implementing order-independent transparency, sometimes you want your fragment shader to be able to write and read to a pixel because you want to maintain this linked lists of sort of fragments to be able to blend them later. And then there's other OIT techniques that rely on this. So if you're curious, look at object-independent transparency techniques. A lot of them want this feature. I'll just skip this. This is just there's like some limitations on storage image that are now more lifted. And then this stuff refers to bindless rendering. I believe we talked about bindless rendering on the Vulkan 1.2 stream, but it was like pre-pandemic or it was like years and years ago, so I don't recall. And we recently talked about bindless on Niagara stream a couple streams ago. So you can kind of refer to this. This doesn't mean bindless is in the core. Like this doesn't mean bindless is required to be supported, but this is like this is getting slightly further into the bindless direction. And then, oh no, wait, never mind. I'm going too fast. This is not even quite bindless. This is just saying, oh, I have an array of. It's kind of related to bindless. It's like the very, very weak version of bindless that you couldn't really use bindless fully. So anyway, let's just ignore this. Realistically, if you use bindless, you want the extensions and you want the features that we've talked about on previous streams. All right, so this is my biggest nemesis. Vulkan has support for YCBCR samplers. This refers to an ability of fetching the pixel from a texture and converting it from YCBCR format to RGB format. This is commonly used for video because video codecs tend to encode in YCBCR, and then some hardware has this capability sort of in hardware. And I heard it saves power. I don't like it because it's such a weird feature that complicates a bunch of core aspects of the API. And it feels like the degree to which the complication happens is not like worth it. And I wish there was a simpler way to do this, but like whatever. And then finally, so more dynamic indexing stuff. Again, it's not full bindless, but bindless is closer. This is not super useful. And this one is the feature that is really valuable. What this refers to is an ability to enable a different packing for your various sort of buffers that you can access in your shaders, and have this packing behave more like C++ and C and less like the shaders used to work. So the way the shaders used to work is they have this interesting rules for how values are packed. And the rules refer to I'm gonna butcher the specifics on this a little bit, but the rules kind of date back to the era where GPUs thought in 16-byte quantities. Specifically, there was the type in GLSL, it's called vec4. In HLSL, it's called float4, right? So this is like your 16 bytes of data. And it used to be the case that GPUs really loved this sort of 16-byte alignment and 16-byte registers. GPUs used to have 16-byte registers in ALU paths in general. Some still do, but most don't now. And so because of these restrictions, when D3D10, I think, shipped, it was sort of the case in D3D9 as well, but D3D10 changed the rules to the rules that most APIs use, I think, these days. And the rules go like this. Every 16 bytes, there is a boundary in your struct that things are aligned to. So for example, if you have a struct with 2 vector 3s, there is a gap here that is 4 bytes. Because the layout rules say, oh, every like field of a struct has to start at a 16-byte alignment. Unless there's special rules that say, okay, actually you can fill these 4-byte gap with a float. So if you have this this layout, this is tightly packed. There's no gaps here because the float doesn't have to start at the 16-byte boundary, but vec3 does have to start at the 16-byte boundary. And then if you have like vec3 and vec2, then again there's a gap here. Or if you have a vec2 and vec3, then there's like 8 bytes gap here. There's two problems with this. So one is this layout, there's many problems with this. This layout is different from how C compiler would align this. This, for example, a C compiler would align this as with like no gaps in between vec3 if the vec3 type doesn't have an alignment requirement. If the vec3 type has a 16-byte alignment requirement, then this would be aligned again differently by the C compiler, because the C compiler, if vec3 has an aligned requirement of 16 bytes, then the C compiler says, well, that's cool, I will not put the float in the alignment padding, I will put it like later, depending on the API and stuff. So all of this is like extremely confusing because you have the same declaration of a structure sort of semantically on CPU and GPU, and they don't map one-to-one. Notably, Metal doesn't have this problem. Metal has a more C-like alignment structure, but Metal has a different problem, which is it doesn't have a way to enable like this crazy layout rule. And so when you port code between Metal and non-Metal renderers, there's also like weird alignment shenanigans. So anyway, Scalar block layout fixes all of this, or maybe most of this. I'm not sure if it fixes like 100%, but it introduces this new set of alignment requirements that's called scalar alignment, which is basically sort of working as a C compiler would work from the alignment perspective, assuming there is no specific, there's no like 16-byte alignment restriction on any struct. So when you use scalar alignment on your structs, it's likely that your layout matches the C++ layout. And you can also stop playing stupid games. So let's say you have a struct. Let's say you want, this is common in like material data. Let's say you want a bunch of colors and a bunch of scalars. So like you want color, like could be like albedo multiplier, like, and maybe separate like emissive color or whatever. So if you lay them out like this, color, 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 and then float, float, and then let's put like 3 more floats. Then each of these is 12 bytes, and each of these is 4 bytes. And you would hope for the whole structure to take 64 bytes, because this is how much data is in the struct. But actually what will happen is every color will be aligned by 16 bytes, and the whole thing will take 16 bytes extra, so like 80 bytes instead of 64. And again, scalar block alignment like fixes all of this, and things behave as they normally do. The problem with this is, unless the feature is required, it's hard to rely on it, because it's difficult to toggle it kind of on and off, because this is how your data is laid out, and so it's hard to support both. But because it's now supported, you should be able to just, if you target 1.4 as a min spec, which is a separate thing that we'll cover in a second, then you can just rely on this and simplify reasoning about all of this stuff. All right, so there's a bunch of limits that are bumped. I don't care to talk about most of them, I don't think, because I don't remember what the minimum limits were in 1.0. So let me just skip this part in the interest of time. What the heck? Hold on. Okay. I don't know. Right. So this are spelled as limits, but it's kind of a feature that Vulkan 1.4 now requires, which is there's some caveats around this, but this is a little valuable. So in 1.1, there's this feature introduced. It's complicated. I believe we talked about this on some stream. Like if you look at my Niagara streams, there was some stream where we talked about subgroups. But in 1.1, they added a bunch of functionality to be able to essentially refer to values that a different shader thread computed from another thread. So, for example, let's say you have a GPU that works in, let's call it 32 thread. The terminology about all of this is a little crazy. Let's just say that on NVIDIA GPUs, 32 threads form a warp. And then on AMD GPUs, 32 to 64 threads form a wave. And you have code that's running in these threads that's sort of independent from each other. Like, let's say each thread computes the calling status of an object. And so you have called status, which is an int. And that you have 32 values of this int at a given point in time. On a GPU unit, it's more than 32 usually, but like it doesn't really matter. Normally, if you think about the CPU execution, 32 threads can only communicate data through memory. And Vulkan has this ability, which is called like shared memory, and you can communicate through global memory, etc. But because GPUs tend to execute these threads in these larger units, and that execution happens more synchronously than you would expect, often it's almost free to ask a different thread from your like warp in this case, what is your value? And so, for example, there's like an operation that you can call that takes all of these integers that are 1-bit integers from each thread, and then converts them to a 32-bit mask. Right? Why is this useful? Well, maybe this is the data that you want to write to memory. Maybe you want to write the results of this process as individual bits to memory. And it's difficult to write individual bits effectively because you have to use like atomic cores and stuff. But if you can take them and turn them into a 32-bit mask and then ask thread 0 to write it to memory, and then other threads will just like do nothing while the write is happening, then things are going to be faster. And there's like a bunch of other techniques and tricks that these features enable. Covering them would require like an entire stream, so we will not do this right now. But suffice it to say, they were completely optional in Vulkan 1.1, and with 1.4, they're sort of required. You have to have them in compute and fragment shaders at least. And there's a bunch of different types. So the thing I was just talking about is kind of ballot. There's also vote, which is a weaker version of ballot that's also super useful. There's also things like, oh, let me take the value from like another thread. For example, all threads can get access to the thread 0. And there's like a bunch of other stuff. But the caveat is that there's still a way for a vendor to ship a graphics driver without supporting this operation. This is kind of the... there's a few famous examples of vendors doing things like this. In Directory 9 days, there was a feature called vertex texture fetch, where a vertex shader could load a value from a texture. And shader model 3.0 required it, but it didn't say, oh, the feature has to be supported for these formats. It just said the feature has to be supported. And there were GPUs that we will not name names, but there were GPUs with a certain color that said, oh, we are totally shader model 3.0 compliant. You can absolutely use vertex texture fetch. The only problem is the list of formats that the feature is supported for is empty. And so this feature has a cop-out like this, where it's totally required to be supported. But if your subgroup size is 1, then these operations will functionally work, but they will be also functionally useless, because I think all of them will be like a no-op, because essentially the subgroup size refers to the width of, it's like 32 here, to the width of this group that you can interact, and like within this group threads can interact. But if the width is 1, then the thread can only see its own results, and so the feature becomes like useless. And so this looks like Vulkan now mandates support for subgroups, but actually it doesn't. And we will skip this. This is floating point shenanigans. We will probably skip, what does this, I don't actually know what this means. Oh, yeah, let's just skip this. This is like a minor DTP11 thing, sort of. And then this stuff is valuable. We talked about this on Niagara streams at some point in the past, but similar to the thing that I was just talking about, where there's a history of GPUs only working with 30, like float 4 units essentially, so 128 bits. The way GPUs graduated from this is they said, well, no, okay, actually we like scalar execution mode now, but the scalar has to be 32-bit. So you can have a float, that's fine. You can have an integer, that's fine, as long as the integer is 32-bit. As you can imagine, this is not great. There's many cases where you want to pack things tightly. And so previously what you had to do, like let's say you have int 8, and int 16. And let's say you want this data to live in memory somewhere, maybe in a constant buffer, on a structured buffer, whatever. What you had to do was you said, oh, actually this is int 32, there is just 1, but then in the shader I will do bit operations on this value to extract individual components. This worked fine for something like this, but then there's questions, oh, can I have an array of int 8s that's like large, like, I don't know, 64K? Can I have 64K of int 8s and then index them dynamically? And the answer was sort of not really, but what you could do is you can, again, have an array of 32-bit integers and then do some bit masks and stuff like this to extract this. So more and more, the common theme here is GPUs are actually just general purpose compute sort of hardware. And of course they have access to 8-bit integers. Of course they have access to 16-bit integers. Like that shouldn't be a thing that you think about when you write shader code. So again, there was a bunch of bits that enabled this separately for separate components. Some of these bits are now required. There's some bits that are still not required. I think, I don't recall where this was. Yeah, so for example, the 8-bit access here says, oh, in storage buffers, you can actually access it. But there's a separate bit that says, oh, but in uniform buffers, this one like is not required yet, right? So again, most implementations, I would hope, for modern GPUs support like all of this, but this is not a guarantee yet. Similarly, push constants, you can ask for this feature to be enabled, but Vulkan 1.4 doesn't mandate it yet. So if you have push constant block, you can bitpack stuff inside it like in a guaranteed fashion. All right, so that's kind of the enabled features. I want to talk briefly about the availability of Vulkan 1.4 before we go into the extensions. Oh, and I skipped this. We'll just go in order in which this post lists things in. Oh, and I do want to talk about this. Okay, so let me just briefly look in chat, but I think by and large, this is a reasonable summary of the features that are now required. I want to talk a little bit about kind of what this means. Other performance considerations with using scalar layout. So it's a little tricky because it's hard to talk about performance without knowing specifically the hardware that you're targeting, right? On most GPUs that I'm aware of, scalar block layout is just fine. There might be complications that make it not fine. For example, I think I recall, let's look at an example of where things might be problematic, like, and why they might be problematic with scalar block layout. So I just talked about this amazing future where it doesn't matter if things are aligned or whatnot, but let's say you have a struct that has 2 vector 3s and 2 floats with scalar layout. And then if you don't have a scalar layout, then this takes more memory, so you probably pack things differently. So you probably pack things like this, right? Okay, so then let's say you have a shader that only wants to read like the second vector, like this guy. So with scalar block layout, and again, this is not a property of, it's kind of a property of how your data is laid out. So if you have this struct, it's aligned the same way whether you scalar block layout or not. And so for this struct, you're going to hit the optimal hardware path regardless. But if you enable scalar block layout and then you forget about these alignment restrictions and then use this, then what the hardware has to do here is it has to fetch this 12-byte value from an offset of 12 bytes. And this straddles a 64-byte boundary because the 16-byte boundary, sorry, because the 16 bytes blocks will go kind of like this. Let's say you have a GPU that happens to have maximum performance when fetching 16 bytes at a time. Well, now to read this vector, you have to read two 16-byte lines and then merge them. On a GPU like this, you would be better off with this layout, or if you disable scalar block layout and you only read this one vector, then again it will be aligned. There are some GPUs where you want to fetch things in 16-byte chunks from memory still. Now, the performance characteristics of not doing this are less and less important. More and more accesses like this go through caches with larger cache lines where 16-byte is not really a quantity that you talk about, etc. So I would say it's hard to have a definitive statement. There's gonna be older GPUs where scalar block layout with unaligned data leads to slightly worse performance. How much this matters, it will depend, right? There's going to be newer GPUs where, it's kind of a difficult trade-off because, okay, let's say you don't use scalar block layout. So the optimal thing to do is like this, kind of guaranteed optimal. But if on GPUs that don't have these weird restrictions, where you use this layout, which wastes space, you might actually be reading more data from memory, and so on these GPUs, you're losing performance, but on some other GPUs you may not be. Anyway, it's hard to make a definitive statement, but I would say as far as I know, people in the industry are slowly migrating to scalar block layout equivalents in directory land, and it's fine. So there might be a couple hotspots where you are losing performance on this, but on modern hardware, I would expect you not to, and it should be fine. Why are these int8 features in Vulkan and not SPIR-V? They are in both. The way this works is to have access to this guy in the shader. You ask for it in the GLSL code. In fact, hold on. It can be faster to show an example. So this, you have to ask for 8-bit storage in GLSL code, and then once you do, you gain an ability to have a buffer. I think some of these, somewhere here inside the mesh structure, is an 8-bit quantity. But then you build the SPIR-V module, and the module in its header says, oh, I want 8-bit storage requirement. Or I want, I'm relying on 8-bit storage to be supported. When you load this blob inside Vulkan, the device has to support this feature, and the feature has to be enabled. And so the capability exists on both sides, and it has to be enabled on both sides to work. So while it is a shader feature, not every SPIR-V shader can be loaded on every Vulkan device. So this is kind of why you see this here. All right. So I keep talking about this, once you switch to Vulkan 1.4, or if your device supports 1.4 or whatever. Some Vulkan releases, like 1.1 if I recall, have been specifically structured such that every device that has 1.0 should be able to support 1.1. For example, because of this on Android, at launch, everybody had 1.0, there was no 1.1. But then after 1.1 released, quickly you started to see adoption of 1.4, well, quickly in Android speak may not be actually quickly, but with software updates to the drivers, devices that supported 1.0 generally gained support for 1.1. 1.4 is not like this. If you have a modern GPU, like a GPU made in the last 5 to 10 years, I would say, well, that's not quite fair. If you have like a DirectX 11 compliant GPU, or not quite 11, but like 11.5 or something like this, I'm not sure where the boundary is, then it is likely that a driver update can support 1.4. But there's going to be some GPUs where they just lack the requisite features. If your GPU, well, this one is weird because there is like, again, so if your GPU doesn't support depth clamping, I think there is mobile GPUs that don't support depth clamping. I don't recall which exact GPUs and stuff, but like not every mobile GPU supported depth clamping. Depth clamping was the Direct3D 10 feature, I believe. If it doesn't support it, then like you can't emulate it in a reasonable way, or it's very, very difficult. It's basically, some features are emulatable, but some are very, very difficult to emulate. Like this one is not going to be emulated, so there's going to be some GPUs that don't support this. So on one hand, this means that if you have a 1.1 renderer, especially 1.1, but even if you have a 1.3 renderer, you might not want to update to 1.4 because this requires not just software support, but also hardware support. On another hand, there is the difference between the Vulkan version that you support and Vulkan version that you can run on. A lot of games that target 1.1 may accidentally rely on some feature, or it can be completely accidental because you have to enable this feature, but there's going to be renderers in the wild that have enabled some of these unconditionally, just because you don't have a reasonable fallback. And they looked at the stats and like it was fine to require it and stuff. For these renderers, supporting 1.4 means that this distance between what do we support in theory versus in practice gets shorter, and that is nice. Also, if there is a new GPU that releases tomorrow, the only way that the GPU can support 1.4 is that it has some of these features. And so in some sense, this is a hardware requirement, similarly to Direct3D 11 or Direct3D 12, that is going to just push the industry, and by industry I mostly mean mobile, because again, most desktop hardware just supported all of this for decades now, is going to push kind of the expectations from the devices forward, hopefully. But yeah, this is the caveat around this, right? While a lot of these features are very nice and some of them are required for modern renderers, it's going to be difficult to... Vulkan versions before 1.4 will be with us for a while. Not just because of mobile, there might also be desktop drivers, for all I know, that still support old hardware on 1.3 that will not expose 1.4 just because you can't. So that's kind of the story here. So this one is interesting, for example, in that regard. Both are, I don't know what the value for this one was before, probably 4. This is just how many color targets you want to render to simultaneously. If you have a deferred render, you might need like more than 4. You should try to avoid using more than 4. There's hardware where 4 color attachments is a performance cliff, and so 5 is much slower than 4, even though 3 is not much faster than 4. But for some crazy G-buffer setups, you might need more than 4. But this value is a little bit more interesting. So when Vulkan shipped, you could have the minimum required number of descriptor sets that a shader stage would have was 4. And this is just based on some hardware restrictions. People ran into this problem a lot during initial Vulkan ports. I don't know if these people are happy now that it's 7, because the same people would now use bindless, where bound descriptor sets are like a much less interesting construct. But part of the reason why people ran into this problem a lot is if you look at Direct3D 11 and early versions of 12, let's call it this, but mostly 11, binding model. Then they had all of these different types. You had textures, and then separately you had RV textures, read-write, which is called also UAVs. And then you had buffers, and then you had constant buffers, and then you had samplers. Nobody can read what I'm writing, but hopefully people at least can understand what I'm saying. Is there more? I don't recall. And then if you try to map this to a Vulkan model, you couldn't really map it 1-to-1 because 5 is more than 4. And so if you use all 5 types, then it's like a problem. Oh, isn't the set... Right, but then it gets worse because I think the max descriptor set is not per stage, it's per pipeline state. And so let's say you had a fragment shader where you had texture 1 and texture 0 and texture 1, and then you had a vertex shader that also used texture 0 and texture 2, but this texture and this texture are different in the 3D binding model. So it was very hard to map this entire space onto Vulkan descriptor sets in a straightforward fashion. If you look at the shader compilers these days, they expose a bunch of weird options that, if you don't know this legacy, make little sense. For example, do I have slang? I do. I don't recall if these are options in GL slang, but I was looking at slang recently and it definitely had them. I mean, DXT has these. Yeah, so you have all of these fancy options for modern shader compilers that essentially allow you to say, oh, for this shader, I'd like to move the binding slots for textures. Instead of starting at 0, they should start at like 8. Just because you're trying to pack multiple different namespaces into one larger namespace. And so you have to play these offset games. And then you have to decide, oh, like I only ever need at most 4 buffers. And I'm going to place it in indices like 0 through 3. And from index 4, I will start textures and stuff like this. So these games are now easier to play. Because instead of the limit being 4, it's now 7. I think the reason why it's 7 is there's hardware that supports 8, but they want the last one for some other features of Vulkan descriptors, so they reserve it. But again, in practice, I think people should be using bindless more or less for modern renderers, and Vulkan 1.4 is kind of like a modern renderer feature, even though it doesn't force full bindless support, I believe. So practical utility of this one in 2024 is maybe questionable a little bit, but I mean, it's nice to see the number go up. And practical utility of this in 2016 or 2018 was huge. So, you know, Vulkan operates in this difficult space where it simultaneously supports hardware with crazy advanced capabilities and hardware with very not crazy and not advanced capabilities, totally not talking about mobile. And so they have to decide somehow, right? If there's a trade-off of supporting Vulkan on dated hardware and performance with Vulkan being still way better than OpenGL or whatever, do you go there? Or do you say, oh no, we don't care about this hardware, it's too old? It's difficult. Timestamps we'll skip, and then some of the stuff I want to talk about. All right, so and yeah, to be clear, again, these features actually all of these features, even this one, but these features, nothing in your C++ code changes. Like you have to enable these, but there's not new structures or functions that these expose on Vulkan side, other than like some features and properties stuff. So it's not like, oh, to use this, you have to change a lot of C++ code. It's just that you have to change C++ code to be able to load new shader modules. All right, so let me close all of this stuff. And let me just open a tab for each of these. Wow, these are slow to open. Oh, each of these opens, oh no. Each of these opens the same URL. And so, of course, it's slow because the file is large. Okay. So what order do I want to talk about these in? So let's start with let's try to pick the order that I think is least interesting first or something like this. I don't know. So this extension is a nothing burger. It, in a sense that this extension by itself, or this feature now, it's now not an extension. Oh, no, wait, sorry, hold on. First, let me talk about just the concept. So all of the functionality that we're going to talk about now, similar to the previous functionality, it was always possible to use, but it required the use of extensions. So for example, you wanted, I don't know, like this line rasterization stuff. You could always say, oh, I want this extension, and then when this extension is present, I'm going to use this feature. These extensions are now promoted into core. There is two types of promotions that you could expect. One is the feature is required to be supported by a 1.4 implementation. This happened with push descriptors, for example, which I'm very happy about, which I'll talk about in a sec. Some extensions like, I don't know, maybe this one? No, probably not this one. Like, I'm sure some of these extensions are exposed in the sense that, or are promoted in the sense that the functionality now doesn't require the use of an extension, but you still have to enable it through like feature bits like this, right? And in some future version like 1.5 or whatever, some of these may become required. Both types of promotions are useful because working with extensions is just a little bit more painful. And if you want, there is value in trying to sort of, there's value in saying, oh, we require support of 1.4, and since we have it, we can now use these features, as opposed to saying, oh, our render is kind of 1.1, but also it has all of these different extensions that it may rely on optionally or sometimes even require them. If you write a bindless renderer, you have to have the bindless extensions, which are now core, but before they were core, you kind of could live in a mode where you sort of technically support 1.1.1, but you refuse to work without this extension. And some games, I think, shipped with things like this. So there's value in promoting things to core because A, it's less code that you have to write to work with this stuff, and two, it establishes a more clear baseline for the requirements that your application has. But for all of this functionality that we're going to talk about in a second, you could use them before. It's just they were optional. For example, Niagara, the renderer that we are writing on a series of streams, from almost its inception required this extension. There was a brief period where I implemented fallbacks for when this extension is absent, and then I removed these fallbacks because they stopped being necessary, and with 1.4 I can stop using this extension. But all of these were features exposed through extensions before. This would be a good time to mention that if you have to use extensions, you should definitely use Vulk, which is a project that I maintain that simplifies loading of extension and entry points and stuff like this. It's not required to use extensions, it's just very convenient. All right, so anyway, so this extension is the least interesting probably of the bunch because by itself it doesn't enable any new functionality. The reason why it's necessary is that when Vulkan shipped, do they have, yeah, when Vulkan shipped, it had a bunch of functions that kind of looked like this. You have a function and it just takes a bunch of arguments. This is a good API design for ergonomics. You want to map some memory. What do you need for this? You want to specify the device, you want to specify a memory object that you're mapping, offset and size, bit mask for future extensions, and it returns you a pointer. Cool. This is good API. The problem with this is that Vulkan relies a lot on extensions, and this API is not extensible. Let's say to map some memory object, you have to pass additional functionality. I'm not sure what exactly that functionality would be. There's like probably already 2 other extensions that are reliant on this, but like let's say you want to use an extension. You can't call this function and pass more data to the driver because this is like the minimum, there's nowhere here other than the flags that you could extend. There's space for more data. And so if you had an extension that wanted to extend VKMap memory, you had to ship a new function, like VKMap memory, I don't know, AMD for some AMD specific extension. But then let's say a different vendor wants to ship a different extension. They also want a different version of this function, so they ship another function. And so in the ecosystem where different people make different decisions at different times, a format that Vulkan gravitated towards was this one, where instead of having the arguments in a function, you specify the pointer to a struct that has these arguments. And this struct, in addition to these same arguments, where is the actual struct? VK memory map info. So in addition to the same arguments that your function takes, they have this stuff to mostly pnext pointer to be able to extend the function calls. I kind of low-key hate all of this because it makes the API less ergonomic while making it more extensible. And unfortunately, this is the reality of that Vulkan kind of has to deal with, but this is why functions like this are being created. So this by itself gives you 0 new functionality, but it allows the use of some future extensions, or maybe some current extensions. Anyway, not super interesting. So then these two. So then another thing that happens more and more these days, and I talked about this, I think, in the 1.3 stream, is Vulkan is not just used as a graphics API for engines to target. It's used as a way to implement other APIs. So there's no shortage now of projects that implement something on top of Vulkan. So I guess DXVK is the most famous example. DXVK is an API that's used a lot on Steam Deck because Steam Deck runs Linux, but it runs Windows games on top of Linux. And Windows games tend to use DX12 these days, and so they have to emulate DX12 with Vulkan. But there is also emulation of like OpenGL. There's also emulation of DX911. There's also some other stuff probably like this. And then there is the other direction that things can go in as well, where you have Vulkan implementation that uses some other API as a backend. I think Dozen is a recent one, which is a Microsoft D3D implementation. I think it's called Dozen. There are some others. Anyway, so the other reality that Vulkan has to deal with is, or like the reason why this stuff is kind of important is, on one hand, Vulkan is trying to provide you a better way to write graphics code. On the other hand, there is still a bunch of code, for example, GL is like a problem, where there's still a bunch of apps that rely on OpenGL. And then the way this works often, or right now, is you have GL, and then AMD maintains a GL driver, NVIDIA maintains a GL driver, Intel maintains a GL driver, and then there's 15 mobile vendors that also maintain GL drivers. And then, you know, you have Vulkan, which again has all of these same implementations, and you think there is just one driver for OpenGL that NVIDIA has, for example, or AMD has, but actually it's like 3 for complicated reasons. So all of this is difficult. And it's tempting to say, oh, OpenGL just doesn't matter anymore. So, for example, vendors should stop maintaining this whole thing. But the problem with this is there's existing OpenGL apps that have not migrated to Vulkan, and you ship a new hardware like hardware line, like, I don't know, NVIDIA ships a new GPU, and the old driver doesn't work on the new GPU because it's different formats, different like bit streams, etc. So they have to maintain it because there's existing apps that are reliant on this. In theory, there's a different world where you go like this. The benefit here is that the vendors focus on this support, so on supporting Vulkan on their hardware as best as they can, and then somebody else focuses on this. This maintains compatibility for the old apps, but kind of maximizes the benefit, maximizes the productivity of vendor work in a sense, because they can focus on Vulkan, not having to split their efforts. However, there's a question of how much do you support in translation layers like this. Do you support older versions of OpenGL, or do you support newer versions? Do you support all of the crazy extensions that OpenGL has grown over the years, or do you only support the core subset? And then there's this question of, does graphics get simpler over time or not? Let's say OpenGL had a complicated feature that is supported in hardware in certain cases. Let's say you're implementing a layer like this. Let's say Vulkan doesn't have this feature. You have two options. We have three options. One is you can not support this feature. The other one is you can emulate this feature. And the third one is you can expose it in Vulkan. The problem with the last option is that the Vulkan gets more complicated because it kind of assimilates all of the requirements from all of the upstream APIs. The problem with the option of not supporting is the app might break. The problem with supporting it via emulation is that the emulation might be slow or very, very, very difficult to implement. And so the app kind of works, but it's kind of slow, and so that's not ideal. So the this extension is kind of like this. Oh, it's not surprising that it's made by NVIDIA. NVIDIA has been famous for supporting CAD really well, and it's famous for all of these amazing features like stippled lines, where you draw a line, but instead of a solid line, it's like this. And there's a whole bunch of different modes, like I don't know what they are, but like maybe you can draw points instead of short line segments or whatever. There's a crazy amount of complexity in line rendering apparently, and NVIDIA has apparently support for this in hardware to make CAD apps work well. And so now you have a CAD app that uses OpenGL, can it even run through this translation layer? And even if you don't have the translation layer problem, you have a question of, okay, I have a CAD app that uses OpenGL. I want to migrate to Vulkan because I want to stop this madness of like either expecting updates for the GL drivers or whatever. But I can't because I really, really, really want stippled lines. So how do you break this conundrum? So unfortunately, the way Metal, I should say, tends to break this conundrum, which exists in Metal as well, is they're very, very aggressive on pushing this complexity to the application and keeping the API as simple as possible. On one hand, I like this approach better. On the other hand, Apple is a unique position where they can do this and a bunch of other people can't. And also, I think Apple in some cases makes choices in this decision space that I feel are just not great, just because they don't expose something that's actually commonplace in the industry, but they have this path that they walk, which is like different from everybody else. So there's trade-offs and pros and cons and stuff, but suffices to say, if you really, really, really want stippled lines, you can now have them with VKK line rasterization, and it's now part of 1.4. It's not required. It's this thing again where wherever the feature bit is for 1.4, let's try to find the 1.4 features. It should be actually here somewhere. One moment. And this is a terrible summary. I think this has it somewhere else. Yeah, so 1.4 has a struct where it declares a bunch of extra booleans, and some of these extensions are essentially assimilated into these booleans. So, oh my god. So there's now 6 new booleans that relate to rendering lines, and you basically don't care about these unless you like are writing a GL driver or you are implementing a CAD app. And these are, of course, optional, because if your hardware doesn't support CAD apps, then it's like going to be hard to expose these. All right, so that was the lines. Another feature like this, which I'm more mad about because it is if you have an application that relies on stippling for lines and you're targeting hardware that supports it, it's like, what do you do other than exposing it? It's very difficult to emulate properly. It's going to be expensive. Your hardware has support for it, so your app will be just much slower. Like, you have to expose this somehow. This feature is unfortunately continuing the trend of features that are being added to Vulkan, where Vulkan took a stance that it didn't want this legacy functionality, but now it's getting legacy functionality back into the core. So what am I talking about? What is this feature about? When you use instancing in Direct3D 9, but mostly 10, instancing was kind of broken in 9. So let's talk about D3D 10 for a moment. D3D 10, I want to say just didn't have structured buffers. I'm fuzzy on the details, but if it did, they didn't work as well. And definitely it's the case in like GL3 and OpenGL-ES, etc. When you work with instancing, you had 2 paths. Maybe you had 2 paths in all of these APIs. One path, so how does instancing work? You have an instance buffer, which you want to index using instance ID. And this gives you object properties like transformation matrices or object colors or whatever. And then you have a vertex buffer, which you want to index using, of course, vertex ID. And this has vertex positions and normals and whatnot. And in your vertex shader, you want access to both. There's 2 ways to implement this. One is in your vertex shader, you actually index the instance buffer using the instance ID. And it's just like explicit in the shader code. For example, well, we don't use instancing here, but we use like a different thing called draw ID, but it's the same concept. Well, you can just have code in your vertex shader that indexes these arrays. The other thing though that you could do, which OpenGL and Direct3D 10 and 11 and Direct3D 12, I think as well, maybe, I forget, gave you as an option is, well, you can, the way you work with the vertex buffer in these APIs before the feature called vertex pooling, which I'm not going to talk about, vertex pooling, is you bind them, right? So you bind the vertex buffer, and then you could also bind the index instance buffer. But if you just bind it as a vertex buffer, then it would be indexed using vertex ID. And so there was this special feature called vertex divisor where it says, well, we are gonna index this in a special mode where we take the vertex ID and we divide it by the vertex count that we expect, or by index count, depending on, there's like a bunch of different modes here. Yes. And then when we bind, when we use the vertex buffer, we are gonna index it using vertex ID modulo, there's not enough space here, modulo the vertex count. And this gives you kind of similar functionality, but it's a very different path. And so you could always emulate this by synthesizing the vertex shader that does the exact same math yourself. Emulation was not always easiest path, I guess, but the other problem is there could be hardware that just didn't support the right thing. And now there is the feature as part of core Vulkan that allows you to kind of use this other mode of instancing. If you look at the actual API for this, let me just show. Yeah, so the way this is controlled is you specify. Oh, this is slightly different from how I remember things being in OpenGL, but it's probably compatible. Yeah, you just specify a divisor. Shouldn't there be a flag somewhere else? This is fine. You just specify a divisor. Oh, this is even weirder. This is like an instance divisor, not a vertex divisor. Right. This is worse than I remember this being. I'm sure this is the exact shape that you need to emulate OpenGL and Direct3D 11 or whatever. I don't think Direct3D 11 had this in this shape, did it? I don't remember. Anyway, it doesn't really matter much because if you're writing a renderer these days, like you should just ignore this. This thing should not exist. The only reason why it exists is older renderers and older hardware liked doing things this way when you use instance rendering. The modern approach to all of this is you have the shader code do this. And the benefits of this are plenty. You can pack data in different ways. You can sub-index a bunch of stuff. Like, for example, if you want to have instancing and skeletal animation, then if you're using a modern approach where the shader just indexes buffers, then it's easy to have the instance data have an offset into some other buffer that stores bone transforms. If you are targeting older APIs, it's much more difficult to do, and with this extension is again much more difficult to do. So unfortunately, this is the trend that Vulkan has a little bit of a split identity, right? Because this kind of solves the problem that I was just talking about using Vulkan as an interface layer between a different API and the driver, but that layer has to get more and more complicated over time to accommodate more and more requirements. So if you're writing modern renderer, please don't use this on any hardware, on any desktop hardware that people still use, and on any mobile hardware of recent years. Like, you shouldn't need this, but there's some old mobile hardware for which this stuff is relevant. All right, so this one I was a little surprised by seeing, but I don't recall if this is a GL feature or not. I feel like it might be for some older GL versions, but basically indices in the index buffer have been either 16-bit or 32-bit for the existence of graphics as I know it, but some hardware used to support, or maybe still supports, I guess still supports obviously 8-bit as well. 8-bit indices is not something you really should need for the most part. If you're using mesh shading, then in mesh shaders indices are 8-bit, but that's a very different type of setup. If you're using traditional rasterization, it feels rare that you care about using an 8-bit index buffer because I don't think it realistically buys you much. Your index data gets smaller, but you can support at most 256 vertices. So do you really care? I'm not sure. However, there is some things that people have been playing with in recent years that this might help with. For example, if you have a mesh shader, it's still going to be a terrible implementation option. Yeah, you know what? I don't think I can argue in good conscience that 8-bit indices in traditional rasterization are actually super useful. I suspect they got exposed because the hardware just knows how to do this, and then vendors discovered that they all have this in hardware, so it's now part of the API. I'm not sure. This thing is very minor. This is just saying you can use 8-bit. Oh, and it's still optional 1.4, of course, right? Oh, yeah, okay, never mind. This is just part of core, but it's probably not required to be supported by hardware. Again, I don't think this is super useful, but this is the type of feature that the only thing it adds is an ability to use an extra enum value on like some APIs. So the cost of this feature is minimal compared to like this instance trade stuff, which is extra structs and functions and extra complexity, which I'm not a fan of. But yeah, the 8-bit index, like, it's fine. So we're gonna leave this for last. I don't want to argue for or against this feature. Let's just skip this. It's not super interesting. For this one, I have to go to the SpearV spec. One moment. I don't really want to talk about this too much because I honestly don't know the history. So there should be a 1. Should be version 1 of this extension. So that adds these guys. I think I must have talked about this stuff on 1.3 stream. What does this add? So the only thing is it adds oh, okay, it does add some new modes. So I don't want to talk about this in detail because this stuff is super like, it's not relevant for the most renderers. It's very, very in-depth, and I haven't actually read this spec before the stream, so I don't want to make any critical mistakes. But to outline the general problem that this extension solves. There is a certain set of optimizations that change behavior around floating point code, but you'd really, really, really like to be able to do by default. For example, let's say your shader code has a multiplication of some value that you compute through complicated expressions by 0. This may happen in practice. This happens in practice often because usually the way this happens is you have A times B, and then B is sourced from like some constants, some logic, etc., etc., etc. And when you compile a particular combination of your shader code, you arrive at the value 0. Maybe this was an emission factor, and this was a sample from the emission texture, and your factor came from the constants that you somehow baked into the shader binary, and so you'd really, really want to completely drop this. So what you'd like to do is you'd like to perform a set of transformations. For example, A times 0 is 0, A plus 0 is A minus A is 0. And then there's some other identities that you'd like to be able to transform. For example, if you have A plus B minus A, you'd like it to simplify to B. Or just as final example, if you have A times B plus C, you'd like to simplify this to one operation that most hardware can execute, which is like FMA. Okay, all of these are invalid. Like 100% of these are invalid. Why? Well, this one, if A is infinity times 0 should be a NaN by the IEEE standards, but you're simplifying it to 0. This one looks harmless, but actually if A is negative 0, then negative 0 plus 0 is positive 0. So you are changing the behavior, you're changing the sign of the output if A is minus 0. A minus A is 0 breaks for infinity. infinity minus infinity is none. A plus b minus a breaks for lots and lots of pairs of floats, like, I don't know, 0.1 plus 0.2 minus 0.1 is actually not 0.1 because of how floating point math works. And then this last one is also different for almost any triplet of floats, for most triplets of floats. Okay, so all of these are going to change behavior of your code, but you'd really like to be able to do them. So because of this, in C++ compilers, there is a bunch of different options that compilers tend to have that go around, oh, do we enable some of these transformations or not? But C++ compilers tend to err on the side of preserving the behavior exactly. Shader compilers tend to err on the behavior of maximizing performance and just, ignoring a bunch of these rules. Who cares about IEEE anyway? But in some environments, you'd really like to be able to say, oh, I want to have these guarantees, but not those guarantees. And so there's like a way to specify a bunch of this stuff in SPIR-V now. Some of this is per module. Like on a module level, you can say, oh, I am not cool with any of the simplification that change IEEE behavior. Sometimes a specific thing is a problem. For example, you would note that around these first two, the conditions for when these are valid are different. This one is valid under a setting usually called finite math, which is to say, if no computation in your program produces infinities, then this is a valid optimization to do. But this one is invalid for a finite value called -0. So for this, you have usually a setting called no negative zeros or something like this. And it doesn't say you can never produce negative zeros. It just says the compiler is allowed to optimize under the assumption that negative zeros are not important. And so all of these extensions are basically about specifying some of these modes either on the shader level or sometimes on an instruction level. Yeah, like you may have 5% of your shader where you really want exact behavior, or you really want to preserve infinities or whatever, but you don't care about this for the rest 90%. So all of this stuff is about changing, about passing this information to the actual shader compiler in the driver that allows us to perform the optimal decisions, hopefully. And for the sake of your sanity, I hope that you never have to apply all of this knowledge in practice, because all of this gets really tricky to actually do in shader compilers. Vendors tend to have bugs around this. Optimization pipelines tend to have bugs around this. It's just difficult. You have this shader and you're testing it on one hardware and it's fine. On a different hardware, it's not fine because the behavior is different. So I hope you never have to care about these, but if you have to, I'm sorry. Okay, two more, and then we'll talk about the biggest two in some sense. This one is huge just because it's a bunch of small things, and then this one I just personally like. Okay, subgroup rotates. This is a minor thing. So I already covered this a little bit when I talked about these subgroup features, right? There is like instructions that do ballot, which aggregates bits from different thread groups. There's instructions that allow voting or arithmetics or whatever. One thing so if you look at these two, this is going from memory, so I hope I don't mess it up. But let's go back to this world where we have 32 threads, and then we want to exchange value between the threads. So for example, thread 0 may want to get access to the value of thread 1, thread 1 may want to get access to the value of thread 2, etc. And then thread 31 may, well, let's ignore thread 31 for a second. So, and I think I mentioned this, but if I didn't, these are computational primitives. Some of them have specific function, but broadly the way to think about subgroup ops is, here's a bunch of ways that different threads can communicate between each other. Now let's figure out what useful algorithms we can build on top of all of this. Sometimes these are more useful, sometimes these are less useful, but for every one of them, it's usually a thing that you can build a faster algorithm with having this instruction because you have access to this extra hardware functionality. So let's say you just want to get values from a different thread. So if you want to have all threads T0, T1, T2, T3, if all of them should get access to the value that's thread 0 computed, this is called shuffle, and I think this is the like this guy. But maybe shuffle is, there's also shuffle XOR. No, but shuffle XOR is not here. Anyway, shuffle relative, I think, is this mode where you say, oh, in every thread, I want to read the value of thread index +1 or +2 or whatever. But in this question, there's in this setting, there's this question, what happens to thread 31? Like, where does it read the value from? So I don't recall what the spec for relative says, but this thing exposes a new operation called subgroup rotate. And the way you decipher this, by the way, is this. So this is an extension, again, just as I was answering this question about why the integer 8 bits are in Vulkan at all, not just in SPIR-V, so they're in both. So this extension, the only thing it does is it exposes the SPIR-V functionality in Vulkan. So to know what it does, you have to go to the SPIR-V extension. And then here, it will say, oh, you have this extra feature called group rotate, which, wait, where is, shouldn't there be the precise, oh yeah. Return the value of the invocation whose ID is within the group, is calculated as follows, and then there's some math here. And essentially what this does is it allows you to say, okay, so in every thread, so for every thread number I, we are going to compute the value that we are going to like copy the value that was constructed by the group, for example, after it. And then to solve this question of what happens with the last thread, we are going to mod this by 32. And then both 1 and 32 are things you potentially can control. Again, I don't know what specifically the application of this instruction is, but apparently hardware has support for it, and so exposing it makes sense. You can emulate this in some cases using the existing instructions, I think, maybe. I'm fuzzy on whether there is a subgroup shuffle that takes like a variable instruction. I don't remember. It doesn't really matter. But this expands the already large list of subgroup instructions with like one more that's some hardware support. Again, just like a lot of the previous stuff we've talked about, this is now part of Vulkan 1.4, but there should be a bit somewhere here. This guy. There's 2 bits actually. I think one is for 1 bit you can control 1 but can't control 32, and then the other bit allows you to control 32 as well. So if you are relying on this feature, it's still not enough to have 1.4 support. It has to be optionally enabled by the hardware that you're targeting. All right, brief pause. It's, oh my god, there's also this one. Oh, okay, that's fine. So brief pause. Let's look at chat, and then we will proceed. Okay. So let's see. Does Vulkan still do GDI bullet when used on Windows without the DXGI swap chain? Was this ever a case? I don't remember this. Maybe this was a case for some specific drivers. I don't know. I don't know the answer to this. I'm surprised this was the case in general. I thought it's not. There are some issues with full DXGI swap chains though, that I don't know if they're fully solved. So I'm not sure. I don't know the answer to this. So what's the advantage of bindless? You can refer to 2 streams. A few weeks ago, I did a Niagara stream where we used bindless, and I talked about this then. Are new profiles a move in the right direction to deal with the huge divergence in device capabilities that Vulkan apps usually have to face? I don't know. So profiles are motivated by the concrete need, so they're well intentioned, but I don't know if people care in practice, because I think in practice people more often say, I wanna build this game. Let's look at the target hardware market. Let's look at the features that people just have always, and let's go with that. So I'm not really sure. Let me rephrase this. I don't know if people use them in practice, and so until they use them in practice, they may be a well-intentioned feature doesn't serve its purpose, right? But they are a move in the right direction for sure. And in a sense, some of the stuff that we are talking about the Vulkan 4 is kind of a profile. It's in fact, I think this is taken. There was a profile called Roadmap like 2022, which was basically if you're shipping hardware in 2022, you better freaking have these capabilities that have existed for many years, right? And so in a sense, it's now Vulkan 1.4 is like a profile because it aggregates the features from this profile into a version of the API. So I think in some sense it's useful, but I don't really know if this will help, because I think the reality is, again, if you want to write a modern renderer, 1.4 is like not enough. It's a good baseline, but you want more features on top of it. So it might be that it's an ever-moving target. I'm not sure. Okay, Roblox questions obviously are going to be ignored. Push descriptors, I'm going to talk about this. Roblox kind of use the scene system from Augur. No further Roblox questions, please. Have any features been removed, demoted from Vulkan? Are we currently on the C++ path of never removing anything? To my knowledge, not a single thing has been removed from Vulkan, unfortunately. On one hand, this is good, because, you want to have the API, like, I don't think this will even happen. Okay, so there hasn't been a Vulkan 2.0. In general, it's a bad design to remove things from patch releases, right? From point releases, from minor releases. So in some sense, I'm glad that nobody removed anything. In some other sense, Vulkan as an API at 1.4 is dramatically more complicated than it was in 1.0, especially if you count all of the extensions that have shipped. But even if you don't, when Vulkan 1.0 shipped, people were super happy because they looked at the OpenGL state. The OpenGL state of things was as follows: there's a lot of different versions, all of them have a lot of problems with performance and stuff like this. Also, there's a ton of extensions on top of all of this, and some of them you want to use and some of them you don't, and it's just hard to wrangle with all of this. Today, Vulkan is in the same spot. It's the fifth version of Vulkan, in a sense, fifth release. There's an insane amount of vendor extensions, there is an insane amount of KHR extensions, etc. And you're kind of in a similar spot. Now, there's a bunch of things that are way better. For example, all of the optional features, you have to declare them. And so you're not in the position where you unknowingly take dependency on something that hardware may or may not have. You knowingly take dependency or don't. And then the extension space is a little saner now. There's less crazy town in some aspects, but if you are hoping for a simple graphics API, Vulkan 1. Whatever ain't it, and it's not looking like it's gonna get there. My personal opinion is that long term this is unsustainable, and that there is a way to fix this. But the way to fix this requires getting a couple more things that haven't happened in Vulkan yet, which I can't talk about, and 2, making an actual breaking change. And that's really hard. I hope it will happen at some point. I don't know what the decision process is gonna look like for something like this. Apple has done this with Metal, right? Now, again, Apple has done this in Metal in the sense that Metal 1 is a dramatic departure from what has been in the past. But I think Metal hasn't removed anything since either. And so Metal is on version 4, if I recall correctly. And I think all of the Metal code that you've written before kind of should still work. And yeah, long term, this is not sustainable. There is possibilities that I could imagine that are somewhere in between 2.0 and the state that we're in right now. Some sort of simplification where there is some profile or something where you don't rely on some of the stuff that has been added. Just, I don't know. I think if I'm being very honest, I don't see this actually happening. I could see some ways to fix this problem, but I don't think these ways have consequences, and I don't think people involved will accept the consequences no matter what. So I think, unfortunately, we are on the path of like more and more code and more features. But you know, yeah, I don't see a great way out of this mess. I am curious. I have absolutely zero inside information on this. I am curious as to what Microsoft is planning with Direct3D, because Direct3D 11 to 12 was a dramatic departure, and Direct3D 9 to 10 or 11 was a dramatic departure. But it's already been many years since Direct3D 12 shipped, so I am curious, like, is there Direct3D 13 ever? Right? Is Direct3D 12 like the last version of Direct3D? But yeah, I don't anticipate Vulkan getting smaller at any point in the future, for now. I will be very happy if this is wrong. I just don't quite see how this will happen. For example, I've talked about this many times before. I think mesh shaders are a dramatic simplification of the rasterization APIs. And they kind of remove geometry shaders, tessellation control, shaders, tessellator, etc. from the API. So that's cool. Can there be a version of Vulkan that only supports mesh shaders? Right now, the answer is no. The answer is no for two reasons. One is not all hardware supports them. But two is a lot of use cases of Vulkan require all of these crazy shader stages. I just talked about DXVK. A big use case for Vulkan right now is Steam Deck, and I guess Linux gaming in general, right? But then you'd end up wanting to run these games that use this feature that you want to remove from the API. What do you do? Emulation is expensive, etc. So I wish there was a clean way out of this mess. I don't know that it exists. So in practice, I don't think things will be simpler. All right, uint 8. No, so see, the problem is with meshlets, you don't need this extension because with meshlets you don't use an index buffer, and this is just about the index buffer. Yeah, I don't fully know why this extension exists. It doesn't seem super useful, but it's fine. Yeah, 8-bit indices are completely fine. Like, the fact that they're in the API, in some sense it's nice because it makes the API cleaner. There's 3 integer types, 8, 16, and 32, and only 2 of them were okay to use for index buffers, and now all 3 are, so that's completely fine. And again, uint data type is very different from the uint 8 index buffer type. I don't know why you want the uint 8 index buffer type, but of course there's plenty of use cases for the 8-bit integers elsewhere. Was the OpenGL situation so dire that Vulkan Orbital has to support all mobile hardware? It seems like a huge missed opportunity for a fresh break from OpenGL to then chase after dynamic state legacy. So dynamic state in particular is a different complication. A lot of the reasons why you see the dynamic state extensions popping up is not just because of the emulation concerns, it's also because of the new software concerns. I don't think there is any other like changes in this regard. Maybe maintenance had something. I don't think so. So I don't think we'll have an opportunity to talk about that particular aspect, but I did talk about this in 1.3 stream like several years ago when that happened. So you could go watch this. Nothing has changed since then. But yeah, it's a difficult question. OpenGL situation was dire. The situation OpenGL ES was in on mobile was this. Drivers were absolutely terrible from the CPU consumption perspective. Like, you would spend an inordinate amounts of time per frame to have the driver do the work that a competent Vulkan driver could do it 10 times less time. And there was no way out. There's various like achieving zero driver overhead type tricks that didn't really work or require some sacrifices or whatever. Like, there was no way out. And so I think Android graphics situation was in a bad spot. Having said this, this is also always a question that you can ask. Do we sacrifice short-term gains for longer-term rewards, right? And I'm not really sure how to think about this looking back. I think back then the decision was very obviously the right one. Looking back, I think you can question it. But looking back, like, you have insight that you didn't have before. So I'm not sure. But yeah, I know there was a lot of... I think an argument could be made that essentially prioritizing mobile for Vulkan adoption has hurt desktop adoption. If you look on desktop today, Vulkan is, on Linux, it's a great API, you use it, right? But on Windows, there's very few games that use Vulkan. Doom, Eternal, etc. uses Vulkan. There is a recent Indiana Jones games. I don't know if it uses Vulkan. It's based on the same engine, so maybe it does. Baldur's Gate 3 has a Vulkan backend. But Baldur's Gate 3, I just watched a video 2 days ago or yesterday from Graphics Programming Conference where they talked about Vulkan. They talked about Baldur's Gate 3 rendering engine. It was not Vulkan specific, but one thing they mentioned is they removed Vulkan support because they don't need it anymore, because they did it for Stadia, and Stadia doesn't exist anymore. So like, I think an argument could be made that putting much more emphasis on desktop would completely, like, mobile would be in a way worse shape today compared to where it is right now, because today on mobile Vulkan situation is like, okay, it's not ideal, things can always be better, but it's not bad. But on desktop, Vulkan is not as interesting because there's D312 and it works much better. And the reason why I'm saying this is early adoption of Vulkan, I think there was a lot of complication because of some of these hard decisions that have been made in favor of older hardware, right? So I don't really know. I tend to think, largely speaking, it's probably fine because there's other things. It's tempting to look back and say, oh yeah, we could absolutely make different decisions 8 years ago and things would be so much better. But actually what would have happened is, even if you did make different decisions back then, is you'd have new complications that you don't see right now, because you only see what has happened, you don't see what could have happened actually in practice. And so it's tempting to have a more pleasant version of the potential future compared to what would actually have happened. So by and large, I don't think it's too bad, but there's like a bunch of things that I wish would be done better. Anyway, Rainbow Six Siege had a stable Vulkan render and they removed it, and I have no idea why. Yeah, so this is the part of the issue with Vulkan is just right now, unless you're targeting Android or Linux specifically, you just don't need it. It doesn't give you a lot of benefits over Direct312 other than being portable. D312 has unfair advantage. D312 is the only, is it true? I'm not sure, but basically D312 is the console API for Xbox. And so if you have a console, and you can't use Vulkan there, so D312 has an unfair advantage in the sense that a game will have Direct312 port if it wants to ship on Xbox. And then, if you already have the D312 port, do you really want Vulkan? I think Baldur's Gate was this situation. They had to have a D312 port to ship on Xbox, which means now they don't have to have a Vulkan port, so they removed it. And I would guess that the Ubisoft, whatever their status is, I would guess it's similar, but I don't know. Anyway, all right, let's keep going. Oh, and we have more stuff to talk about. I don't really want to talk about these two because they're weird. some DRM stuff, I think. Yeah, I guess I have to talk about this one. This is nice. I will talk about this. And then this is maintenance 5, maintenance 6. Okay. And then streaming transfers. All right, we are getting there. There's a few more new things to talk about that are important and valuable. Wait, where was the... one moment. Yeah, okay. And then this one. Okay. Load store of none. This is a pretty simple thing. And people who used Vulkan may be familiar with the, well, let me just open the this enum. It's going to be easier. So whenever you work with render passes in Vulkan and you start a render pass, you have to say, what do you want to do when you start rendering to the specific image that you're rendering to? Do you want to load it from memory? Do you want to clear it, or do you not care what happens to it at all? And this is important, well, as in you don't care what the initial state of the image should be. And then there is a parallel enum on the store path where after you render to an image, you say, do you want to store the results to memory, or do you not care about doing that? The reason why this exists is because of tilers for the most part, or part of the reason. It also is helpful in some cases, rarely for non-tilers. But the big reason is mobile tilers. And this is because when you when you render geometry on a lot of mobile hardware, most mobile hardware, it does this in these chunks called tiles. And so you have your screen, it's like split into tiles, and then the hardware looks at this tile, which you can't see probably. The hardware looks at this tile and says, okay, I can identify triangles that have to be rendered here, let me do that. And the reason why this is valuable is they have on-chip memory that's very fast, but there's not a lot of it. And so you can store the small fraction of your frame buffer in this on-chip memory, render a bunch of triangles to it, and then copy this back into main memory. But these copying operations are slow comparatively. And so if you can avoid them, it would be nice to avoid them. For example, if you, before the era of compute, let's say you do post-processing, like this is the simplest example. The way post-processing works is you want to render into a target, but you only ever render a full screen quad, right? That just writes the pixel, the value of every pixel to its output. Usually you want a full screen triangle, not a quad, like it doesn't matter. If you don't tell the driver that you don't care about the initial contents of this memory because you are going to render a quad there, so that will overwrite it anyway, the driver doesn't have enough information to know this. And so what the driver might have to do is it might have to load the data from memory, which is slow. You could say, oh, clear it to white or whatever, or to black, which on mobile is actually faster than loading because it doesn't eat global memory bandwidth. But then the problem that you have is that on desktop hardware that doesn't have this special tiling stuff, you cleared a target just to then write data back to it, which is also not ideal. So because of this, from 1.0, you have to say what you want to happen. But the don't care bit is interesting. So the way don't care says it doesn't matter what happens. Like I can accept any result. And there's cases where you want load to be, how do I put this? Let's say, what's a good example? I need to come up with an example for this probably. Um, The examples are a little complicated, they require exposition. But in some cases, there was this problem where you wanted to say, how do I put this? You knew that the buffer would, oh, yeah, right, yeah, okay, yeah, I remember the good example. Is it a good example? There's cases where you want to have a guarantee that the value of that the values in memory will be preserved. So let's say you render geometry, and let's say you do this to color plus depth. But let's say depth buffer is not actually being used at all. For whatever reason. So you bind color and depth, and then you render triangle, but the rendering result doesn't affect depth. So depth value, like depth test is disabled, depth right is disabled, depth doesn't matter. But the buffer is bound. So if you specify don't care for depth, you actually run the risk of having incorrect rendering results on some hardware, because don't care doesn't say what happens to memory, it just says anything goes, and the behavior on tilers and on non-tilers can be different there. On desktop, usually don't care means don't change things, and on tilers, usually don't care means whatever garbage is in some memory, just keep it there. And so none allows you to say, I promise I will not use this buffer at all, even though I'm binding it, but I want to have a guarantee that whatever was there before the pass started is also going to be there when the pass ends. And this is a stronger contract, but it's also sort of faster in both cases, because for desktops, it's usually roughly the same, but for mobile tilers, I guess mobile tilers are a little bit. For mobile tilers, it's sometimes more expensive than just load store, but it's less. But it's like more correct that don't care if you actually want to preserve the value. Anyway, so I don't know if this made any sense. I'm just struggling to remember any use cases for this that are interesting, because I think in many cases when this actually happens in practice, you could rework your code to not need it, but it may be difficult to do so. Anyway. All right, let's actually talk about the more interesting stuff. Well, let's skip this because this is not interesting. So let's talk about the more interesting stuff. Okay, so robustness is valuable, and this extension is also valuable. What does this all mean? When Direct3D 10 and 11 shipped, they had really strict guarantees about what happens for out-of-bounds accesses to various objects. Because in Direct3D 11, you can have a buffer that you bind to the shader, and in the shader you say, oh, I want to read buffer element I. Or you could say, I want to write to the element I. And then the buffer has a certain size, and then this question is, what if I is larger than the buffer size? Direct3D 11 shipped in the era where Windows cared a lot about security, and so they really wanted very strict guarantees about what happens, because what you could say is, well, it's a programming mistake for I to be out of bounds, so if you write past the buffer bounds, just write somewhere in memory, maybe a GPU crashes, maybe it doesn't, maybe you corrupt some data, maybe you don't. This is terrible for security, because this means you might be able to read data from memory where some other process wrote it. And of course, it's not great for the correctness of your code either, right? So Direct3D 11 has strict rules. Effectively, the rules say if you read out of bounds, you get 0. If you write out of bounds, the write gets ignored. If you have hardware functionality for handling this way, then this extra safety that you get for it might be free. But if you don't, it's not free. On a lot of mobile hardware, and probably on a lot of desktop hardware that, even if it does support Direct3D 11, you didn't have an option of just toggling a bit in hardware somewhere to say, just ignore out of bounds writes on these resources. So if you wanted to guarantee that this semantics holds, you have to, in the driver, like instrument the shader to guard against these. So, oh, you are writing to the buffer and the index is I. Well, the driver may add something like I, if I is less than buffer size, then do this right. Obviously, if you never write out of bounds or read out of bounds, these extra checks each time. So in Vulkan, the way they solved this problem is they added this feature. This is Vulkan 1.0. They added this feature called robust buffer access, and also this should be, one moment. Somewhere there's also robust image access, I would think. Anyway, whatever. There's a ton of language on what the guarantees are. But basically, if you specify this, so this is just for buffers. I don't remember what the image semantics are. But this says if you do buffer accesses and shaders, if you set this to true when you create a device, then the driver will guarantee that these accesses are safe for the definition of safe broadly that we talked about, like writes do nothing, reads return zeros, etc. If you set this to false, then there's no guarantees, anything goes, and whatever happens is kind of your responsibility. Essentially, you have to kind of promise the driver your app doesn't do these accesses. So, as I mentioned, for vendors where all of this stuff is implemented in hardware, enabling this, setting this to true might be free. But for vendors where it's not free. And the problem is this is an all or nothing on the entire device. Like when you create the device, you just say either all access to all buffers and all shaders have this property or they don't. Sometimes in practice you want, for example, you have some specific algorithm that you know that you don't know, like you don't know if the accesses there are in bounds always or not. And so you kind of want this extra guarantee, but maybe for some other shaders in your process, you do know that nothing extra needs to happen for them. But the only option that 1.0 gave you is to say, oh, all shaders are already good or all shaders are bad. And this extension allows you to toggle the same bit on just a single pipeline, on a single pipeline stage even. On a single pipeline stage. And then you can do this separately for images and buffers and all of this. So this is like way more fine-grained than the original extension is. From the list of contributors, I would guess that there is like some hardware stuff on like mobile GPUs. There's some non-mobile stuff, non-mobile people here as well. But I would guess that essentially on some mobile hardware, it's like really expensive. If you are writing a render, in general, the recommendation is you do not set this value to true because it's like a performance penalty on some hardware. But the problem is sometimes you don't have great options because the bad case here looks like this. You ship an app with this value setting to false. Driver doesn't enforce robustness at all. You ship an app and then you get GPU crashes in the wild, and there's no way for you to debug them because it's not like there's not like an address sanitizer for this. The sort of is, but you never ship with it. So the bad case looks like you shipped an app, you get crashes in the wild, you don't know where they happen. And if you run the same shader code in direct 3D land, it works perfectly well because there the guarantees are upheld. So there's probably cases where it's convenient to set this on some specific pipelines. Maybe you're porting shaders from like a different API, and you set them for some specific like shader. There's also probably cases where, I don't know, I'm guessing there might be cases where maybe in compute, the compute hardware has robustness built in, but the fragment shading hardware doesn't. But your app doesn't care about the fragment shading kind of robustness. So because like the shaders are already guaranteeing this implicitly, so there's all sorts of like out of bounds access behavior where stuff like this is important. Similarly to the floating point extension, I will make a comment that I hope you don't care about all of this stuff and you can just have shaders that don't do out of bounds accesses. But I think the current unfortunate reality is setting this value to true for all shaders is safe, but may cost you performance on some hardware. So that is that. All right, so then there's two maintenance extensions. The way maintenance extensions work in Vulkan is like this. They want to fix a small problem in an API. And, you know, you ship an extension to fix a problem in Vulkan, right? But the problem is like really small. Let's find something really innocuous, like this one. This is like a thing you don't really care about. It helps applications to not rely on features that they are not enabling implicitly or explicitly or whatever. But it's like a minor behavior change. And for example, let's say you think in practice the implementations are already conformant with this, but it's just not been ever in the specification. It's not been written in the specification. Or like let's look at this thing, for example. Whenever you do image operations in Vulkan, you tend to work with the structs that say what data do I copy, what data do I read from, stuff like this. And Vulkan 1.0 said you have to specify the MIP level. Let's say you're copying from a texture to a texture or something like this. You have to specify the MIP level, the layer you start from, and the number of layers. Technically, if you are copying an array of size 4, for example, you have to specify 4. Let's say you want to copy the whole texture, like all of the layers. You could say basal layer is 0 and layer count is set to what exactly? There's no single value, right? And Vulkan 1.0 forces you to be explicit. It forces you to say exactly how many layers you have. But of course, the driver has access to the total number of layers in the texture, like you're passing the object, so of course it can read it from whatever internal structures are there. And so it could trivially implement a feature where instead of the specific number of layers, you specify this magic value and the driver reads the number of layers from wherever and then uses the correct one. This exists for some values in Vulkan, but not for others. So it didn't exist for layer count, but it did exist for MIP count somewhere else. Buffer sizes sometimes have this. Let's see. Like, there's a similar thing called VK whole size, which was valid in most cases where you talk about buffers, but apparently not in bind vertex buffers. So there's like this small problem that you want to fix, and fixing requires making an extension. But if you made an extension for every bullet point on this list, that's a ton of extension, and that's a lot of process overhead, because you making an extension requires, I guess, like voting on it, or whatever processes have to happen inside whatever group works on all of this. Like, people would probably stop working on Vulkan if every new sentence like this added to the spec required a new extension, because it's just too much bureaucracy. So the way this works is they have this maintenance extension, which we're already on number 5, and then there's number 6 here, that fixes a bunch of small things. I definitely don't want to talk about every single one. Let me talk, is anything super interesting here? It's unlikely that any of these extensions will fix the problem that you really, really want it to be fixed in general, just because like this is not how things work. This is a little interesting. This like exposes a thing that you couldn't. Oh, this one is big. This one is big. Okay, I want to talk about this. Not big. Oh, actually, I guess this is the answer to somebody was asking if any features were removed or deprecated. Well, not removed, but at least we got the deprecation in. So I will talk about this. Nah. Some of these are nice. I just don't want to spend time talking about this. I'm already a little tired and we haven't gone through the rest yet. So let me just talk about these two and this one. So this one, the reason I picked this one is this is a feature that people may not be aware exists that is important for performance in certain cases. So we've already talked about tiled rendering. And we've already talked about these bits that you should provide to the driver where you know what should happen with the contents of memory before or after. One other bit that might be of interest to the driver is what is the bounds that you're going to be rendering to. Is it the whole render target or this is some specific section? This comes up in some cases and is valuable in some cases. Let's say you're rendering shadow maps and you pack all shadow maps in like a big atlas. This is very, very common in production renderers, like Roblox does this. Like everybody does this probably. Not everybody. And the reason why you pick an atlas instead of texture array is you want to pack multiple different things of different sizes together and you don't have bindless capabilities. Let's say you reserve some space for your shadow cascades, and then you have a bunch of point lights, and some of them are very small, so they use very small fractions of the texture, and some of them are much larger, so they want much larger bits, and like this is kind of your layout, right? This is your shadow map atlas. And you don't want to re-render the whole thing every frame, that would be expensive, so you pick the lights that move, you prioritize them somehow, sometimes you like reallocate them to different sizes within this atlas, etc. So then there comes the time to render a light. And then you say, okay, I want to update the shadow cascade for the sun in this frame, like this one. So I start rendering to this texture, and then I render a bunch of geometry. And then I have the viewport and scissor set up to limit the rendering to this specific area. So unfortunately, and on desktop hardware, you're done. On some mobile hardware, this is not enough for peak efficiency, because if the driver doesn't know that you're only going to render to a small subsection, it may still load and store every single tile from memory and back, even though you're not changing most of them. Some hardware optimizes these things like this for free, like because in theory the drivers sort of can. Some hardware has capabilities that allow it to be able to not have this. For example, my recollection is that Metal doesn't have this feature in the API at all because it doesn't need it. But in Vulkan, there's a feature called render area. That allows you to say, I want to limit the rendering. I am making a guarantee to the driver that my rendering is limited to this specific area. Please optimize based on this. In practice, on tilers, what happens is instead of loading and storing every tile from memory and back, only the tiles that are inside the render area get covered. However, there is a question, which is, can this area be completely arbitrary? Can it be like 5 by 5 pixels? And the answer is it could be, I guess, but where is this function again? But some render areas are not optimal. The optimal render areas are aligned to a given size. This is usually the tile size of the hardware. And if you knew what the requirements would be, then when you did your render atlas, your shadow atlas like layout, when you picked which lights go where, it would be fairly easy for you to just align things to these sizes. Maybe the sizes are 16 by 16 on some hardware and 64 by 64 on other hardware, and it's okay for you to align to 64 by 64, but you don't know you have to. So this extension allows you to ask what is the, oh my God, I lost it again. This function, I should say, which is now core, just allows you to query this rectangular region dimensions, and it will return, you have to tell it like the format and stuff. So ability to get access to this information, I believe, existed before, but it required the use of render pass objects. I already talked about this in 1.3 stream, I think. Render passes are dead, long-lived dynamic rendering. So now you can query this information for dynamic rendering. This essentially covers the, in general, dynamic rendering should be free from the GPU perspective, as in anything that you could, any optimizations that you could invoke with subpasses should also be invocable with dynamic rendering. And this covers like an instance where this was not the case. All right. And then shader modules. Shader modules are deprecated. So it's a minor thing. It doesn't like matter a whole lot, but it does make one feature that has been deprecated in the Vulkan. So a reminder to people who forgot how Vulkan works with shaders. There's like a bunch of extensions now that change the paradigm, but the way this works is you have sphere V, which is just bytes, and then you create a VK shader module for each one. And then you take a bunch of these, because you have vertex shader and fragment shader and whatever, and then you create a pipeline state object from it. I guess it's called graphics pipeline object or something like this in Vulkan. When Vulkan was specified, the idea was the driver does a bunch of work here, here, and then the application, like if you create one shader module per sphere V and then use different modules in multiple pipelines, then the driver does as much work as it can here. And then whenever it creates PSOs, it takes whatever the internal representation is for the individual sphere V blobs, optimizes them together, compiles them into this beautiful set of shaders that are performant. It turns out that this step is useless. Like, there is almost nothing you can do here in the driver that helps anything. You can compute the hash of the sphere V blob, which I guess is cool, but hashing algorithms work at like tens of gigabytes a second. So like, this shouldn't matter too much. But nothing important can happen here, because for anything important, the sphere V blob is not enough. You have to specify a ton of extra information for the sphere V blob for it to be compiled to hardware. Even basic things like resource access. The sphere V blob says, oh, it's descriptor 5, slot 17. But this value is meaningless to the hardware. The only way to know where this actually should go when you're compiling the shader binary is to know the layout of descriptor sets, which is a separate object that you don't specify when creating a shader module. So like most drivers, I would expect do almost nothing when you create a shader module from sphere V. There is a couple of cases where it's valuable to cache work. For example, when you have debugging layers enabled, the sphere V to shader module step can do sphere V validation, which is expensive. But it's trivial to cache the results of this validation work by hashing the pipeline and then doing the validation if the hash has changed. And there's this whole pipeline cache stuff that kind of sits on top of this anyhow. And so the upshot of this step is kind of not needed. Like, the driver doesn't do anything useful there. And so because of this, you don't have to create the shader module objects anymore. You can just feed the sphere V bytes to the pipeline creation functions, and it's the same thing. And it actually reduces cost in some sense, because the one thing the driver did have to do is to copy the speed of E bytes to some internal driver memory when you called this, and now you don't have to do this. So anyway, this was just like a thing that I guess people were hoping would be useful, but I think the whole space of pipeline state objects was not fully understood when Vulkan 1.0 was created, and so this step ends up being basically unnecessary. And so, you know, you don't have to use shade modules anymore. This is a step that simplifies future code, but doesn't really matter for the current code, because if you are maintaining the code for Vulkan 1.3, it's not gonna be like, this feature is not worth upgrading to 1.4, obviously, right? And it's just not like super interesting. It's a small thing, but the hope is enough of these things compound. We saw 1.3 basically deprecate. So I guess I wasn't quite correct either. Frame buffers are basically deprecated as well. Because even if you use render pass objects, you don't have to use frame buffers because there is like imageless. Some aspects of frame buffers. So if you ask me, then I guess frame buffers and render passes should be considered deprecated, but I don't think they officially are. And shader modules definitely are now, so that's good. All right, and then there's the second maintenance extension, and then we'll take a brief pause after this. That probably is just not. Eh. Oh. It's actually kind of funny. So we just talked about map memory 2 extension. For that extension, they made like a whole extension. But for this one, they did 2 versions of a bunch of other things that, anyway, it's a little weird. None of this is like super worth talking about. This one is like funky, but like, why do you want this? Again, I'm not fully sure. None of this is super interesting. Okay, let me look at chat. Yeah, I'm gonna talk about dynamic rendering local read. I wonder why the designers went so far to support existing hardware rather than draw a line. Again, like I already said this, right? You make a choice, and then the question is restricting the short-term gains worth the long-term potential gains? If Vulkan didn't support, let's say Vulkan hardware requirements were such that most mobile hardware didn't have these capabilities, then Vulkan doesn't become a thing on Android, and now Vulkan is a thing on Android, just because nobody cares about Vulkan on Android if hardware doesn't support it. So some markets just move very slowly. Okay, I already covered this. I don't know if dozen is related to Xbox, I'm not sure. DirectX has superior debugging tools. And it's more stable. So more stable is more true. Drivers for DirectX are kind of rock solid to the extent that drivers can be rock solid. Drivers for Vulkan are getting better. They're not always great. Vulkan has a few really annoying stability problems. One problem is Vulkan has an official layer mechanism that means applications like OBS or whatever can just inject extra code into your app. This is an official sanctioned functionality. A lot of these layers are broken, as in a lot of them will break your code just because they're not written like very correctly. Debugging tools, I'm not sure that's true, because everybody uses RenderDoc, and RenderDoc works really well on Vulkan, so. Who actually has it on hardware, AMD and NVIDIA? I'm not sure what the question is. AMD and NVIDIA is about. Is it possible to disable the robust buffer access on DX, or is it always enabled? I think it's always enabled, but remember DirectX targets a smaller hardware range. For example, DirectX only recently started caring about tiling hardware because Qualcomm is shipping hardware that you can run Windows on, right? But I don't think you can disable robust. But it's kind of an interesting problem. It's again this short-term, long-term thing that is interesting. So there exists hardware where wherever this thing was, there exists hardware where the hardware itself doesn't have a feature like this. Well, it's actually complicated. There's two aspects of robustness. One can be fixed in hardware, one can't be. The one that can be fixed in hardware is if the hardware just doesn't support robust buffer access, and so the shader compiler has to add an if statement. The other thing which is more interesting is buffers could either be pointers or pointers plus sizes. And so even on hardware that supports this feature in hardware, the descriptor for a buffer has to accommodate this buffer size for robust buffer access to work. And I think this is actually on some hardware, the Vulkan Boolean can change the descriptor allocation, whether it has the size or not, even on desktop. And on DirectX, like I don't think you can disable this in DirectX. But I guess there is some aspect in which DirectX forcing people to live with robustness requires vendors to optimize for it, if that makes sense. Like whatever hardware didn't have this feature before probably has it now because of DirectX, like the future generations of the hardware. But yeah, this one specifically affects the descriptors for buffers. And so maybe there is a way in DirectX to somehow disable it. I'm not sure. I'm not an expert in DirectX, but I didn't think there was. Yeah, I should say for all of the stuff that I say about Vulkan, from my perspective, OpenGL has been deprecated years and years and years ago. There's reasons to write production code in OpenGL. There's always reasons to write production code in anything. But I have personally ignored OpenGL for the last many years. The only renderers like Roblox still have to use OpenGL because they still really care about older hardware that doesn't have stable drivers for Vulkan or doesn't have Vulkan support period. And on macOS, there's still some fraction of the hardware that doesn't have Metal. But I think it's like, from my perspective, OpenGL is a legacy API and has been for the last, I mean, not since 2016, because Vulkan was still like in an odd shape, but I feel like for the last 5 years or so, OpenGL is like the legacy API. You only target it because you must, not because you really have to. The caveat to this is, if you're teaching graphics programming, Vulkan is like difficult to teach. Maybe WebGPU is like a better long-term version for stuff like this than OpenGL. But yeah, anyway, okay, so we are back to we are down to 3 things that we have to talk about. Have I missed anything? Yeah, there's just 3. Okay, cool. Okay, so let's talk about dynamic rendering local read. This is exciting because this, to my knowledge, fully covers the gap that was left when dynamic rendering was specified. I don't want to rehash the whole why dynamic rendering is important again, because I did this in Vulkan 1.3 stream. People should watch it. I personally was a very big proponent of dynamic rendering. It happened because a lot of people I don't want to overstate my involvement, because a bunch of different people argued for it, and because the actual work involved in shipping dynamic rendering is a ton of work by a ton of people. It's probably a list is 100 people. This is just for this extension, that have to do specification work, driver work. It's not always clear if things will work out, etc. But I was very loudly against render passes early on, for a few reasons. When Vulkan shipped, a lot of people looked at Vulkan and asked, why does Vulkan need render passes? This is stupid. This is a mobile feature. And it should have been an extension that you don't have to care about when you're writing desktop render, etc. I don't agree with this take, but I do agree with a different take, which is the stance I had, which is render passes are a leaky abstraction, and that abstraction leaks so much that is not useful. When you're writing a renderer that doesn't have to support mobile tiling hardware, etc., to the extent that mobile hardware, so this tiling stuff that I was talking about, it gives you extra capabilities if you want to optimize for this hardware, in theory. When you do the classic example is deferred shading. So you do deferred shading when you render to gbuffer, and then after this you run a few passes that read from the gbuffer, compute shading properties of the pixel, and then write the color back. And normally on tiling hardware, this requires rendering the whole thing to main memory. The gbuffer tends to be fairly large. It's a bunch of bytes per pixel, and so the bandwidth cost is very large. So you write a bunch of data to memory and then you read them all back. Instead, in theory, what you want to do is, after you render geometry, you want to run some code for every tile that runs these shading computations, but everything stays in this on-chip memory segment. And this is the thing that you couldn't do in OpenGL without some extensions or Direct3D. But if you didn't care about that particular bits of functionality, then render passes were kind of actively harmful, because they required managing a whole lot of state in a way that was in a way that interfered with a bunch of practical concerns when you're writing a game engine. And so they just got in the way. And then the second problem with render passes was that when you did want this capability and this optimization and stuff like this, render passes promised you that the driver would do an optimal job. But A, they didn't tell you if that was the case, and B, there was a class of things that you looked at the API and you thought, oh, the API allows for this optimization to happen. But then you asked the graphics vendors, oh, does your driver do this optimization? And they told you no, and it can't be done because such and such. And so it was an abstraction that was harmful for you when you didn't care about optimization because it got in your way. And it was harmful for you when you did care about these optimizations because it would give you a false sense of security. Sometimes it would not deliver you this optimization, etc. So dynamic rendering in 1.3 only addressed the first half of these issues because it only solved the problem for cases where you don't care about this stuff. To my knowledge, this extension, which is now 1.4, addresses the second half completely, in the sense that I think there's now no code that you could write with render passes that can't be ported to fragment shading without losing efficiency in practice. And they now have the feature bits somewhere. No, not here. Hold on. In 1.4. Yeah. And in 1.4, they split the capabilities that the hardware actually has and show it to you in the properties. Because, for example, one of the things that I was talking about just now, where the API promises you have this feature but you don't, is the multi-sampled interactions. I'm not going to talk about this in detail, but suffice this to say, you looked at the render passes and MSA, and gbuffer rendering in tandem, and you thought, oh, I can make a really, really optimal render pass thing that will compile beautifully on target hardware, and then it doesn't work. What you want to do in cases when it doesn't work is you want to actually disable multi-sample anti-aliasing because the cost is too steep. But you didn't know you were under this false sense of security in a sense. So the actual features that this enables, I think, are the same as what you had for render passes. Let me double check this because I haven't validated this. Yes, I don't want to cover the use of this too much because, yeah, I think this is the same, broadly speaking. Yeah, and then you use pipeline bearers instead of subpasses. Yeah. And then that's it. Okay. Yes, I think this is the complete replacement. I would need to think about how maybe the way MSA didn't work at all for anybody is if there's a resolve in the middle, the hardware might just not support this. Yeah. So basically, I think with this extension, the status quo is like this. If you had code that used render passes before, you can convert it to not use render passes and to use dynamic rendering plus this extension if you needed mobile specific stuff. If you can't convert the code, like let's say you had code that had one render pass and 15 subpasses, and you can't convert it to one render pass with dynamic rendering. To one, it's not called render pass anymore. I'm not sure what it's called, like rendering bracket section. If you can't do it, you have to break the passes, but the driver, all drivers were doing this behind your back anyway. And so you change the code and you may feel bad. Oh, I had one render pass and everything was optimal before, but now I have 5. But actually you always had 5, you just didn't know about this. So, so this makes it more explicit, and to my knowledge, you don't really lose performance in any practical cases like through this rework. And with this, as far as I know, we can basically declare render passes obsolete unless you target versions of API that don't support, dynamic rendering at all. So if you target 1.1, 1.2, like you still need to use render passes, I guess. If you target 1.3 on desktop hardware or 1.4 on mobile hardware, basically can ignore them. So that is good news, because that means the API this is, I think, the way that things should have been implemented to begin with, because instead of enforcing an abstraction that doesn't work on you, the API gives you a tool that you can optionally use, but if you don't use this tool, your code is not getting more complicated, if that makes sense. Having said all of this, I haven't tried to use this extension in practice, so maybe there's some specific driver stuff that I'm not aware of. But the impetus is this. This is the completion of the dynamic rendering work as far as I'm concerned, because it completely supplants render passes with other functionality. And I think that's all I want to say about this. Oh yeah, and the way render passes worked with these features in the past is when you were compiling the pipeline state objects, you had to specify the render pass object, which is part of why this abstraction was harmful to begin with, because the render pass object was only necessary for a couple bits of information in actual practice, and it was difficult for the app to give the correct one. There were these rules of compatibility between render passes, like it was all a mess. Now, if you want this feature, you still have to specify extra data when compiling pipeline state objects, and it still complicates your pipeline state management like because you have to keep that in mind. But it's the minimum complication. It's the complication that has to happen for hardware for you to take advantage of this hardware capability, as opposed to this architectural complication where, oh, we happen to have an object that we think will be useful, so we'll just pass the object. So I think from this perspective, it may not drastically simplify the amount of work that you have to do, but it kind of guarantees that all of the extra architectural design bits are kind of out of all of this, and this is kind of how it should have been, I think, to begin with. Worth noting, Metal doesn't have render pass objects, but it has render pass begin and end, and it has a more powerful but more hardware-specific version of this dynamic thing. DirectX 12 used to not have any of this, and then it gained support for render pass, begin and end, again, no objects. And now it also has something that seems somewhat similar to this stuff, but I don't know full details because I haven't read the D3D12 specs. Okay, so that is that, and then push descriptors and host image copy. I mean, if I was making an indie game and I really wanted to write graphics code myself, I still wouldn't do it in OpenGL. I'm not sure what I would do it in. WebGPU is fine as far as I know. It's a little... WebGPU is probably strictly better than OpenGL, I would say at this point, but I wouldn't use it as a replacement for Vulkan or Direct3D12 or anything like this. It just has a bunch of features that are missing. It has a bunch of extra overhead. My understanding is CPU overhead of WebGPU is substantial, but I don't think it's more substantial than OpenGL, so... Oh yeah, SDL3 GPU might also be nice. I haven't looked into this, but I know some people liked it. Yeah, WebGPU shader compilation story is ridiculous. It's like this for a reason. It's a stupid reason. It should never have been like this. From this perspective, actually WebGPU does support SPIR-V inputs if you use the DAWN implement. So if you use WebGPU on the web, you have to use WGSL. But the web is a difficult compilation target to begin with. If you use WebGPU as a native API, basically to just simplify this whole API mess for yourself, you can use SPIR-V shaders. It's fine, as far as I know. Yeah, so if you're targeting the web, things are painful anyway, but anyway, I think WebGPU is fine. As far as I know, it's pretty good. I wouldn't necessarily I wouldn't advocate that everyone switches to it or anything like this. It has a place, but just to give you an example, this Niagara project that I've been working on and off for years now, is completely impossible with WebGPU, completely impossible, because it doesn't have multitude of features that WebGPU has. You have to go through very contorted emulation paths that are actually pretty slow. So not everything that you can do in Vulkan is going to be possible efficiently with WebGPU. But if you want to work on a game, and if for some reason you don't want to use an off-the-shelf engine, you should probably use something that helps you, like WebGPU. Or it doesn't have to be WebGPU, so there's SDL3 GPU now. There's options like BGFX or Sokol that wrap all of this behind easier to use layers, stuff like this. So there's options. And WebGPU is by no means magic, but I would basically treat WebGPU as a library that wraps a bunch of graphics APIs in a single, nicer to use graphics API. All right. So push descriptors and host image copy. Push descriptors. This is another extension that I feel personally invested in. Because while I had nothing to do with the original extension, I argued for making that extension core. and unfortunately it didn't happen for many years, but now it did. I'm not going to talk about what happened, but suffice this to say, so this extension got into it was done alongside this extension, which ended up in 1.2, and this extension ended up in 1.4. So there's reasons, I will not go into why, but what does this, but like I'm happy that this extension has made it, even though it complicates Vulkan even more. But what does this extension do? So if you wanted to pass constants to a shader in Vulkan 1.0, you had basically two options. You had push constants, or you could put the constants in most likely a uniform buffer and then bind that buffer, okay, and then bind this buffer to the shader. So then if you looked at the how do you bind buffers or images or whatever, then Vulkan 1.0 had descriptor sets. Okay. Now, since then, the picture got much more complicated, but there is like a thing that is missing here, where if you wanted to put constants inside a uniform buffer, you had to manage the buffer space yourself, you had to bind this buffer somehow, there was this special offset, dynamic offset stuff to make it faster, etc. But essentially, this was the uniform buffers were the path to bind a bunch of complicated data to the shader, and push constants were a path to send small amounts, small bits of information to the shader. But on the descriptor path, there was only the long way around, where descriptor sets were objects that you had to allocate, you had to manage, there's a lot of complications associated with this, etc. There's two problems with that. One is any code that you write in Vulkan around descriptors is complicated. You have to create a descriptor pool, you have to allocate, you have to update, you have to manage this memory across like GPU frames and stuff like this. The second problem is that on some hardware, you had a concept of kind of like push descriptors. In the sense that you could have a descriptor, there would be like a small amount of descriptor memory, just like there is a small amount of push constant memory on some hardware, that you could just write descriptors to before the draw call and have the shaders use them. And that functionality was not exposed at all. So enter push descriptors. This was the extension that was authored by a person who works at NVIDIA, from which I would infer that NVIDIA has some special hardware like this, but I don't really know. So one problem with push descriptors, how do I put this? Let's say you're trying to choose between using descriptor sets and push descriptors. The choice isn't always push descriptors, just as the choice between push constants and uniform buffers isn't always uniform buffers or push constants. For one, push constants and push descriptors operate with a limited amount of memory. Push constants are now this was the limit, by the way, that was bumped in 1.4, which I'm really happy about. Push constants used to be 128 bytes, and now they're 256 bytes minimum. So 256 is good for a little bit of data, but it's not good for like, you know, your entire scene description, or sometimes if you're putting like a transform matrix into push constants, you can afford to store like, it used to be 2.5, and now it's like, I guess 5. But it's not a lot of space, right? And the more memory you use, so even though the limits, the 256 byte limit is now larger, some hardware doesn't have that much memory available for free. And so if you cross some magical threshold, then things might be slower. And if you actually had a lot of data that you wanted to pass to the shader, then you really wanted to use uniform buffers, because you are less reliant on the driver to manage this memory for you. You can cache data between different draw calls. You can upload a bunch of data to a uniform buffer and then use it in 5 draw calls. Whereas with push constants, you'd have to resubmit it every time. Similarly, with descriptors, a similar logic might apply. I'm trying to use careful language because not all hardware even has this magical push constants or descriptors bits. Some may have push constants but not push descriptors. For some, push descriptors is a pure emulation path where instead of you managing descriptor memory, the driver does it. But the driver usually has, the driver can do this in a reasonably good fashion. So. If you have, your takeaway shouldn't be, I have an object uses a material, the material uses 7 textures, let me just use push descriptors for this. But there's a space where push descriptors are useful. For example, let's say you do post-processing, and then you submit a bunch of draw calls for post-processing. You could allocate the descriptors for these post-processing calls out of a descriptor pool and manage this and all of this. But it's just redundant, like there's no benefit of doing that at all from the CPU side, because there's nothing to share that's very productive, it's not a lot of work, etc. And then on the GPU side, if hardware had faster descriptors that didn't go through descriptor sets, you'd kind of want to use them. And if they didn't, then it's not worse than the descriptor sets. So it's like there's contexts in which push descriptors are just fine. And then there's contexts in which you really want to think about, I have an object and another object, and I render them and they reuse the descriptor set. I should really allocate the object once and then fill it, because that's more optimal on GPU and CPU and stuff like this. Now the descriptor space and the constant space is more complicated. On constants, there is this thing called inline constants, I think. Inline constants. I don't remember how they're called. Yeah, this guy. This is ext. It's now core in 1.3. So in 1.3 added an ability to specify inline constants inside the descriptor sets, I guess. Right? Yeah. And of course, we also now have descriptor buffers. So now there is many options for you to choose from, and it gets a little bit complicated to talk about which one is best. But the reason I like push descriptors is twofold. One is I think it can be convenient to mentally split both constants and descriptor sets into 2 large buckets. One is, here's a little bit of data on few draw calls or dispatch calls that I just need to send the data to the shader. Just let me send the data to the shader, please. I'm running a compute shader, and the compute shader needs access to 5 textures and these 100 bytes of input data. Let me just pass this to the API. And this other path where you're dealing with tons of uniform buffers or tons of descriptor sets. For both of them, for each of them, I think it's useful to have an API feature. One is this more immediate mode, just here's the data, just use it. And the other one is this more retained mode, which is I want to be in control of how the memory is managed. I expect a large amount of data. I want things to be very optimal and stuff like this. To me, so descriptor sets make it complicated, because descriptor sets are this other abstraction that is difficult to map to different hardware features, because it's like, it means too many different things to too many different vendors. But I think broadly, you could think now of this space and this space as being a little similar. Push constants give you a way per draw call to specify little bits of information. It is not the optimal path to manage large amounts of information. It is not always perfectly mapping to hardware, because 256 bytes is not the number of bytes available on some hardware. They just emulate this behind your back if you ask. And then if you have a ton of data, or if you want to share data between draw calls or whatever, use uniform buffers. If you want to specify a few descriptors to run the compute shader or a multi-draw indirect call or whatever, just use push descriptors. It's fine. The driver will manage whatever it needs to. Maybe the access will be faster in the shader, maybe it won't be, you never know. And then you have tons of memory, tons of descriptor memory. You want to allocate it, you want to manage it, etc. You use descriptor buffers. Unfortunately, this descriptor buffers aren't even in core. Don't know what will happen with this. And then there's inline constants, which are, I would say, like, there is a different mentality which inline constants come from, which is you should manage everything through descriptor sets. And then if you want small bits of data, embed them as inline constants. If you want large bits of data or dynamic data, put it in uniform buffers inside descriptor sets. So I would say there is like, there's two different kind of thought paradigms that you could have, and inline constants are more from the paradigm of descriptor sets are cool, let's put constants in descriptor sets. So anyway, that's kind of my perspective. Different people may disagree, different vendors may disagree, etc. But I think the reality is essentially push descriptors became an extension in 1.1, and then unfortunately didn't get into 1.2 or 1.3, but fortunately got into 1.4. So if you have a 1.4 renderer, then you can just pretend they exist. And you might have small performance benefits of some hardware in certain cases, but the big thing I am interested in is simplifying the mental model and having clear tools for clear use cases and deprecating like all of the other tools. So that's what I will say about push, and then there's one final thing that I want to talk about. So all drivers have bugs. For example, push descriptors had a bug in Molten VK that was recently fixed. But Molten VK doesn't even support 1.3 yet. So this is another difficulty, by the way, about these new features that these new versions that I should have talked about. If you try to use Vulkan on Mac, right now the only option to use Vulkan on Mac is to go through Molten VK. Molten VK does not support 1.3. We're talking about 1.4. 1.4 shipped like a week ago. It would be unrealistic to expect Molten VK to support it. Although I should mention that basically if you work on Linux with Vulkan, then for any vendor now, you can just pull Mesa, build it from source, and you'll have a 1.4 driver. Because support for 1.4 has been merged for the open source AMD driver, RADV, the Intel driver, ANV, the NVIDIA driver, NVK, and some other drivers, but there's only 3 desktop vendors, so like 3 is enough. So there is some precedent for getting very, very early support for 1.4. Oh, and if you work on Windows, then NVIDIA has a beta release of the driver. I don't know if there is an AMD support for 1.4 on Windows yet. So while precedent exists, of course, asking Molten VK to support 1.4 today is unrealistic, but they don't even support 1.3 yet, and it's been couple of years since it's been standardized. So I think this is the difficulty with 1.3 and 4. If you want to work on Mac, there is a bunch of issues that you run into, but one of the issues is Molten VK just doesn't support these versions. I don't know if it will. I don't know what the status of Vulkan on Mac will be going forward, but this is the thing to keep in mind. If you were hoping to ship your Vulkan code on Mac OS by using Molten VK, then all of the stream is irrelevant to you because 1.3 and 1.4 functionally don't exist for you right now. Unfortunately, I tried porting my Render Niagara to run through Molten VK while I was traveling. There was a bunch more problems than just Vulkan versions. I would just call it this. And it's basically not meaningful right now to do so. So Vulkan versions are not the only thing in existence. But yeah, obviously drivers may have problems, and yeah, pulling an extension into core is a stronger requirement from a vendor. And one important thing, and I forgot to mention. While most of the stuff that I talked about that was new, all of this promoted stuff, a lot of this is optional. So this thing is optional, this thing is optional, this thing I think is optional, not sure about this thing is optional, not sure about these things, maybe, I'm not sure, not sure about this thing. But the push descriptor is required to be supported. You still have to enable it because in Vulkan you enable features that you use. But if you target Vulkan 1.4 min spec, then this picture is actually, well, if you target 1.4 as min spec, then descriptor buffers are out because it's an extension. So unless you want to use extensions, you can't use them. But all of the other 5 ways to pass data to the shader exist. They exist in core. You can use them. I think, am I wrong about inline constants? I might be wrong about inline constants. One moment. Because, yeah, it's promoted to 1.3, but unless it's required in 1.3, then you can't rely on it having. It might be that inline constants are not required. Oh my god, this HTML takes forever to load. This is annoying, and this is why profiles or features like profiles might be useful. Because even to find out if a thing is guaranteed is non-trivial. Okay, we found, oh, but I can't. I doubt that it's required. Is there a way to whole words? All right, so this page is super slow, as you can probably tell. If I click on this thing, will it get me to the right place? No. Okay, search is not cooperating. I assume that it's not required to be supported. I'm not 100% on this, but I assume it's not. If I'm right, then the guaranteed versions in Vulkan 1.4 to work with data that's passed to the shader is this. The top 4 ones, which again is good because you can rely on this. If you make the choice of only targeting 1.4, you can just say, I am going to use push descriptors, push constants whenever it makes sense, and otherwise I'm going to use uniform buffers and descriptor sets when it doesn't. Okay, Final thing, host image copy. So Vulkan, and they kind of make a big deal out of this. It's like a headline feature, but it's kind of sort of sensible. So they have a headline feature called streaming transfers. So one problem that every Vulkan renderer has to deal with is loading data into the GPU memory. And for buffers, there is a range of options. I don't want to fully describe the space, honestly, I'm tired at this point, but there's a bunch of options for buffers. If you work with buffers, there is always an option for you to map the buffer to memory as persistent. On some GPUs, you then have to copy it. On some GPUs, you don't. Like, it's complicated. But for buffers, you can always, because you control the layout for buffers, because the buffers are your memory, kind of. They're not your memory, but they're your memory layout. You can always copy. Not copy. Like, there's always a way for you to solve the problem of uploading data to the GPU in an optimal fashion. For textures, it's not quite as easy as this. So for textures, the only flow, you can sort of technically create a linear textures. Linear textures are not very useful because not every texture can be linear. And most textures, in fact, cannot be linear. And there's other problems associated with them. So practically speaking, since the creation of Vulkan, the only way to manage texture memory was like this, or the only reasonable way. You create is the wrong word. Let's just say you upload image to buffer. And this is where there's some options. You can just pre-allocate a bunch of scratch buffers and use them. You can allocate one large one, you can allocate a bunch of smaller ones, you can maybe create them on demand if you really need to. There is option. And then you have to schedule a buffer image copy. When I say schedule, what I mean is it's a GPU copy. So you have to have a command buffer that this command goes to, then you have to execute this command buffer. And then I left 2 because, of course, to actually have the copy work, you have to have the image be in the layout that works for the copy. And so you have to also actually schedule layout transition. And then there's actually one more step 2, because the layout transition, you can work without step 4, but like usually you need transitions before and after copy. So why is this a problem? In general, it's not a big problem in some cases, but it isn't a problem in others. So there's two situations that I think are useful to consider. Oh, and all of the discussion is in the context of, if you have to do this once when your app starts, like, it's fine, things are fine. But imagine a complex renderer that streams textures in and out, and so you have constantly new texture assets coming in. You're rendering your game, and then there's new textures that you have to copy. So there's 2 issues associated with this. So one is, what if you are on a device with a unified memory architecture? So and then the other one is, what if you are not? So the other one will call, for example, tGPU. So the first case is when the CPU memory and the GPU memory are allocated out of the same memory sticks, if you were to call them that, as in they sort of live physically on the same device. It's just they are in different address spaces. Examples of this are any integrated graphics on desktops, or I guess on laptops mostly, right? Whether it's Intel or AMD. Of course, all mobile hardware is UMA. And that's it. And then you have the DGPU case where you have host memory and device memory. They are on different devices, and so you have to copy. There's no way for you to not copy. So on unified memory, the fact that you have to do this scheduling and upload and copy is just bad or suboptimal to begin with, possibly. Because usually the way this works is there is a streaming system that streams in bits from the disk, and then you could, in theory, stream them directly into wherever they need to go. But sometimes they have to be format changes associated with this, so that's not always possible. But regardless, the fact that you have to have the GPU perform this copy into the GPU memory is unfortunate because it's trickier to schedule it. You're rendering a frame, the frame takes 15 milliseconds to complete, right? Do you just copy a bunch of textures when the frame begins? Because that means that you are possibly not meeting your frame time budget, because now you have this unknown amount of extra copy work that has to happen on the GPU timeline. And because it's the same memory space, you do have access to this memory space, in the driver at least, from the CPU, and the access is cheap. It's the same device. You don't have to schedule anything. And so it would be nice if there was a way to just directly copy the bits from CPU host memory to the GPU memory that's still the same memory. And this copy might have to do some sort of transformations on these bytes because the layout is not quite the same. But sometimes these transformations are fast. You could sometimes, depending on the GPU and stuff, depending on the layout requirements and stuff, run this copy at memory bandwidth. And so all of the Vulkan mechanics of scheduling transitions and copies and all of this stuff, they're just like not productive. They are interfering with your ability to, at maximum performance, upload textures to the memory that the GPU can then render from. So this is the UMA side. On the DGPU side, you have to do this copy. There's not an option of not doing this copy because you don't want to read textures from host memory every time. So you have to do a copy. And the copy kind of has to be on the GPU. It could, on some DGPU systems, you could also do the host side copy, but there is more complications associated with this. But the big issue on the DGPU side is this issue of frame time management that I was talking about. You have a timeline where you render objects. You have a queue that you submit rendering commands to. And if you put the extra copy operations on this queue, you are making the frame time longer, unpredictably so. And it's kind of guaranteed that you're delaying the actual call. Like, it's a guarantee that you're hurting your frame time, you just don't know by how much. Because copy has to happen. And because of the queue semantics, it kind of has to happen before the graphics work can continue. On a lot of desktop hardware in practice, what you can do and what you should do if you're making a streaming renderer, etc., is you have two queues. So one is called graphics queue and one is called transfer queue. And some hardware exposes a dedicated transfer queue that the only thing it can do is can copy images. Some hardware just can expose, for example, two graphics queues, but both queues can run transfer commands. But if you have two queues, then the optimal thing you can do is you continue using your graphics queue as usual, and then your transfer queue only has these transfer commands, these copies and transitions, and your hope is that the GPU has special hardware that runs this copy for you, and it has to interfere to some extent with the performance. Like, the transfer isn't free, but it's as parallel to the rest of the graphics work as possible. So you're impacting the frame time the least. So with Vulkan 1.4, two things change. One is there is a new facility that addresses this need. So I'm happy that this happened. Again, this I can claim very little credit for, but whatever small voice I had in that, I voiced this before this happened. but this is now a capability that the driver may expose. And you should generally hope that the vendors that work with integrated GPUs like mobile, Intel, whatever, expose this, but vendors that don't work with integrated GPUs may not expose this or may expose this. It's, you know, it's kind of a coin toss. There's cases where it makes sense, but there's also cases where it doesn't make sense. So you can't rely on this always being there, but this is an optional part of 1.4 now. And just to give you a flavor of the extra features here. So you have, this is like a possibility that now exists if the driver exposes this, right? And this is kind of OpenGL style, I guess, buffer, like texture image, whatever it was called, text image 2D or whatever. It's a copy command. You pass it the host pointer and the image in host memory, so you manage the lifetime of this. And of course, you don't do this on your rendering thread. That would defeat the point. You do this on some background streaming thread that's completely parallel to everything else. Your IO request finishes, you queue command to some copy thread that you have, that you manage yourself. You can have two of them if you want to, you probably shouldn't. And then when this completes, the data has magically migrated to this image object in whatever format is best for the driver. This may be expensive on some drivers and cheap on others, but if you run this on a separate thread, on a separate core, it's least disruptive to the rest of the application. And the other thing that you have is this ability to transition, like image layout transitions. And hopefully this function doesn't do actual work, but it sets up the API bits in the right way. But sometimes maybe it has to do actual work. I don't want to cover this too much, just to say that this alone isn't enough, because when you create an image, you can only create it in a useless layout state that you can't, like, that's not, you can't render it using this image. So you have to do a layout transition, but this extension now allows you to do this layout transition like before the copy or after copy on host. And also I think when you create an image, there should be a way to create an image in a more useful layout. I don't recall where this is. Maybe this is not. Maybe you can't do this because you can just transition on host. I forget. Anyway, so this is one option that you now have, depending on the driver. And for example, the difference with OpenGL that is productive here, one of the differences at least, is this can run in any thread. And the application is supposed to synchronize access around this image. Like, it's not defined to use this image while the copy is running and things like this. So you don't run into any of the weird, OpenGL ran into a lot of weird synchronization issues with some of these copies. And also OpenGL ran into the fact that you had to do this on the main thread, unless you used multiple contexts, which is the whole other gnarly mess that we will not go into. And this extension doesn't have any of these problems. So this is now part of 1.4, but it's an optional part. So device may expose this, but it also may not expose this. And this should cover this aspect comprehensively. And if you are on this side of the puzzle, then the optimal thing to do is still to use the transfer queue and to schedule transfers in parallel with the graphics work. But Vulkan now requires this mechanism to be implementable with 1.4. Before 1.4, and this is the, if you look on streaming transfers, you can see that the requirement of Vulkan 1.4 conformant implementation is that either you have access to this host site image copies, or you have an additional queue, so you can't just expose one queue, you have to expose two queues, and the second queue must support transfer bit. And also it says that you can always transfer. Whoa, I was not aware of this at all. This implies that before Vulkan 1.0, it was possible to ship a device that supported graphics and compute, ship a driver that exposed a queue that had graphics and compute capabilities, but not transfer. This would break most Vulkan applications that I know of, so that is funny. But okay, anyway, so this essentially means that any application that targets 1.4 can rely on either the fastest possible DGPU friendly option being available or the fastest possible integrated GPU option being available. So this is the theory behind all of this. I don't have access to the hardware that has a driver that exposes this extension, so I wasn't able to try this extension when it shipped, so I don't know what the status is going to be in practice going forward, right? But this is the idea, and this is why this is called as a streaming transfer specifically feature, because the difficulty that you want to solve is scheduling these transfers in such a way that minimizes the disruption to the rest of your application to the extent possible. All right, I think that is all of Vulkan 1.4. I think 1.3 took like 4 hours, and this took like 3 hours. So that I guess officially makes 1.4 simpler than 1.3. Well, the relative delta between 1.4 and 1.3 is smaller than the delta between 1.3 and 1.2. What is, I didn't talk about, oh, there was an extension that I skipped. I'm sorry, people. I will not, was there an extension that I skipped? Interesting. Okay, that's kind of cool. That interlaces nicely with the thing I was just talking about. When you have these two queues, graphics and transfer, if you use it in transfer queue for streaming work, it's generally work that's not time sensitive. Like if you pick between, do I disrupt my frame time more, or do I have my transfers finish slower? You always pick the latter one. Essentially, this means you want to run graphics work with the highest priority, but if there is bits of unused time in the graphics work, you'd like to use them to satisfy transfer requests. And this extension, which is now core, actually allows you to do this, because it allows you on the queue level to say this queue is normal priority and this queue is low priority, which is useful for this kind of work, because, and again, like nothing, there's complications with hardware implementation around all of this, so there's no guarantee that any of these things work ideally, but the best you can hope for is you can say transfer queue is marked as low priority, which might mean that you need 2 transfer queues now for high priority and low priority. It's kind of weird, but maybe that's fine. And then you hope that the hardware and the driver cooperate to do the best that they can at like uploading your image in reasonable time. And I should say, when you go this route, then you of course have to use synchronization with Vulkan events and stuff like this, with Vulkan fences and stuff like this, to know when the transfer has finished. So the flow is you schedule a transfer, you put a fence, and then you poll on that fence, for example, every frame. And if the fence has finished, then you say, cool, the copy has completed. I can now use this texture in a streaming context when rendering my next frame. Okay, all right. It is related to resizable bar, but it is, no, yeah, it is. So when you have rebar, rebar generally relates, I think, to the ability of essentially marking like all of your GPU memory space as like being writable from host or something like this. So I would expect that rebar helps with implementing this left part of the puzzle. As in, I kind of split this into unified memory address space and non-unified DGPU. But this is not quite true, because again, you could implement this host image copy on the GPU in certain cases. And I think existence of rebar kind of makes it more likely that it will happen. So they're like related a little bit, but they're not rebar is not a prerequisite necessarily. And it's definitely not a prerequisite for this stuff, but it helps this stuff. All right. Do you happen to know of a good reference material for implementing a frame graph that includes memory aliasing? It's the hardest programming problem I've encountered so far. I mean, I'm like, there's a set of classical resources for frame graphs. There's the original GDC presentation by Yuri O'Donnell for Frostbite. There's the Granite Render blog post. Maybe there's like some others, but I don't know. I don't know of a canonical one. And also, yeah, I guess I'm surprised. There's two aspects of memory aliasing. One is which resources do you alias, and then one is how do you correctly place barriers around this for Vulkan and DX312 and stuff like this. The latter part is hairy. The former part shouldn't be that bad. But yeah, anyway, I don't know. I don't know that there is one blog post specifically that I would recommend. For Vulkan, I think the Granite post went into a bunch of details, if I remember correctly. Oh, yeah. Isn't render pipeline shaders like work graphs? Or a precursor to work graphs? I don't recall. Let me see. Yeah, so this is the problem with both of these is streaming textures or resources, whatever, it takes bandwidth. It kind of doesn't matter. So I said here, oh, you just put the streaming on a background thread and it's just fine. Well, the actual problem sort of is, let's say this thread is on another core, but you might run into issues where streaming still reduces the time that it takes your CPU code or your GPU code to run on a system with unified memory, just because bandwidth is a finite resources that is shared between all consumers on the system. Sometimes there's gating, like CPU gets access to like a quarter of bandwidth and the rest is reserved for the GPU or whatever. But even if it's gated like this, you may slow down your CPU workloads on other threads or whatever. So streaming is never like free, right? But the goal of all of this is to make it possible to absolutely minimize the interference with the rest of the system by the streaming work, whether it's the GPU or not. Okay, so I think we are there. If people have more questions that they can submit in the next couple minutes, I will answer them, but I will end the stream in like less than 10 minutes because I'm tired, and we have covered the entirety of 1.4, which is great. Before we end, and before I answer any questions in chat, if people post them, practically 1.4 isn't quite ready for you to try, but you could try it if you're adventurous. So there's no 1.4 SDK yet, which means that if you need validation layers or whatever, you might have to build them from source. But there is a tracking issue. I think it was on Kronos group, Vulkan docs. There's a tracking issue for 1.4. So there's no SDK yet, but if you wanted to, you could build all of the components of the SDK yourself. So if you want validation layers, you can build those. Loader isn't really necessary. You just need the driver anyway. So that usually comes with that. The shader compiler stuff basically didn't really change because the SPRV version is the same. I think the only change in GL slang is you can now specify in command line that you're targeting 1.4, but it's the same as if you target 1.3. So like all of this is the same. There's headers. Vulk is supporting this. If you target Windows, you can use Vulkan 1.4 driver not Windows. If you target NVIDIA hardware, you can have a driver that you download from this page. If you target AMD or Intel on Linux, you can build Mesa from source. If you target AMD on Windows, I assume you just wait for, or Intel on Windows, I assume you just wait for some future driver release. I'm not sure how these work. And that's kind of it. So you could like upgrade to Vulkan 1.4 without too much fanfare. I will do this at some point with my rendering project on stream, maybe, but maybe not. I'm not sure. The to frame this discussion, sort of, if you had a 1.3 render, how do you, like, what does it take to upgrade to 1.4? If we look at the the only work that you have to do is either remove workarounds for the features that you wanted to use before but were optional, or removing the use of some extensions because they're now core. So if we look at our code, we like request a bunch of features in the renderer from the other series of streams, just like because we want them, because we need them. And some of these are now required to be supported. So for example, we really want anisotropic filtering. Technically, this code was not valid before because it would never run on a Vulkan 1.3 implementation that didn't expose this feature. So technically, you had to check before if you have access to this, and if not use it. But now we can just, like, this line of code is now correct once this code gets updated to 1.4. In terms of extensions, so this is the list of extensions that this renderer uses. This is still an extension. It's kind of funny. This one is the push descriptors that I just talked about. This is now part of core. So this can be removed and some code can be slightly simplified. Ray tracing is not core. So that's the same. Mesh shaders are not core, so that's the same. And also the one thing that can be simplified is removing the use of the shader modules because they're deprecated. You can just not use them, etc. Oh, we do use scalar block layout. Oh, that's interesting. I was paranoid about writing all of the code so that it's compatible. I must have forgotten that we started relying on this a while back because I was writing some code on the last stream, I think, and I was paranoid about the block layout, but I guess I don't have to be anymore. That is good to know. I forgot about this. But yeah, so like this line of code is also, it was not fully correct before, and now it is. This line the same way. Yeah, it's hard to show the impact of 1.4 on this code base because this code base tends to be a little bit fast and loose with what features are required versus optional. And also 1.4 is a smaller update. I think 1.3 was a big update because of dynamic rendering, and then bindless is big and stuff like this. But 1.4 is a smaller update. All right, let's see. Yeah, validation layers do not emit deprecation warnings. Right now, there is not enough features to warn about. But I expect maybe at some point. So one way to, I don't know how helpful these things are. One way you could try to address the Vulkan complexity problem is to steer people into the blessed subset. And so what you could do is you could say, let's say there's some subset of Vulkan 1.4 that we consider good and some bad. But bad doesn't mean you should never use this feature because there is emulation context, etc., when it's valuable, and more like we want to establish the best practice Vulkan, and have this be opinionated, as in geometry shaders don't go there, right? Stuff like this. In theory, you could write a layer, a Vulkan layer that warns on any feature that is not in this blessed subset. And in nothing prevents anybody from doing this, nothing prevents Cronus from doing this. There's kind of a similar concept, which is there is a best practices layer already in the validation layer, which tries to warn against performance issues and stuff like this. But there's always this question of, does it help people to have this layer? Because the features that are not in this layer are being relied upon. So it's not fully clear. But I think it might be an interesting idea to have some sort of, Vulkan, I don't know, simple is a bad word because for some people it implies, just too simple. But maybe there is some Vulkan pure subset, and there's some like stamp of approval that's like, okay, cool, my renderer is compatible with Vulkan pure. Yeah, I don't know. Nothing prevents anybody from writing a layer like this today. I think the question is more like, what is a subset that we consider good, and what are the criteria for how features make or don't make it into that subset. SDK will be released in January. Thank you, Steven. That is good to know. Yeah, texture streaming, the way I described it, just deals with the problem of how do you stream stuff. There is also a question of what do you stream. There is different solutions to this problem. Sometimes, and you can, there is sampler feedback. It's not core, but somewhere within, isn't it just called the same thing? I don't recall. I think that I thought there is a way to do sampler feedback with basically similar functionality in Vulkan to what is available in Direct3D12. I don't remember. I will not be able to remember that right now, but sampler feedback stuff is kind of heavy-handed, and there is simpler ways to do this. There is ways to predict which MIP levels of which textures you're gonna need on the CPU, and this is how people have been streaming textures for decades now. It's not optimal necessarily, but the thing that sampler feedback doesn't give you is sampler feedback gives you a solution to knowing, how do I put this? Sampler feedback tells you, I wish I had this MIP level right now because rendering this MIP level would actually give me the correct image. That's cool and all, but the thing you actually want the answer to is what are the MIP levels that I will need in a couple seconds to have a very high probability of rendering the image at a good resolution. And that's a very different question that you can't use GPU. GPUs don't have predictive power. And so the only way to gain predictive power is to have a content pipeline produce a richer set of data. And then you usually run into the problem where if your prediction is too aggressive, you stream in too much stuff. And so there is some hybrid between this that you actually usually need. But yeah, this is a whole separate kind of worms that the last time I've worked on the texture streaming system predates shader image, image sampler feedback, because this was in PlayStation 3 days, so I don't know what the current reality looks like. Okay, yeah, my recollection for best practices is also that the layer hasn't been updated recently, but I might be wrong. But yeah, this is complicated. For Vulkan to be a production-ready API, it has to grow features that you don't want people to use, but they're necessary there, right? But it is an interesting question as to how you evolve the API. And I think, again, one part of all of this is difficult to appreciate unless you've been following this along is, so this whole descriptor stuff, which is kind of messy. But this is the evolution process. When Vulkan 1.0 shipped, descriptor sets existed, but push descriptors didn't. And then inline constants and descriptor buffers didn't exist. And kind of as Vulkan went along, some new the space became more defined. People understood better how to ship software in that space. And so I think in some sense, of course, the problem is this best practices set is always evolving. But yeah, it's an interesting question. If there was a layer that guided people away from older functionality with some longer term hope being deprecating it fully somehow, that might be interesting. Anyway, okay, one final question, if there is a question. There was no question. Yes, we have answered everything. Okay, so thank you everyone for stopping by. Obviously the recording is going to be on YouTube. The Vulkan 1.3 version shipped a few years ago, so probably Vulkan 1.5 stream is only going to be years down the line. Unless something happens, there is going to be a stream next week, probably. Is next week? Yeah, okay, next week is still fine. Where we actually write code. But that is it for today. Thank you for stopping by.